Close your eyes gently, if you feel comfortable, or simply let your gaze soften, allowing your awareness to expand beyond the immediate surroundings. Take a slow, deep breath, feeling the air fill your lungs. Then release it slowly, letting go of any tension you might be holding. In this moment, there's nowhere you need to be, nothing you need to do, no answers you need to find. This is simply a space to wander, to wonder, to let your mind drift through the grandest concepts the universe has to offer. Perhaps you're lying down, gazing up at the ceiling, or maybe you're simply resting, the world outside gently fading into a soft hum. Wherever you are, whatever time it is for you, know that you are safe, you are present, and we are about to embark on a quiet journey together. A journey not through physical space, but through the vast, awe-inspiring landscapes of scientific discovery and cosmic imagination. Tonight, we begin our gentle exploration not in the distant, unimaginable reaches of the universe, but surprisingly close to home, yet a place of profound cosmic drama. We're going to turn our attention to a patch of sky, a subtle blur beneath the iconic belt of Orion, the Hunter. You might have seen it on a clear winter's night, a faint, misty smudge, easily mistaken for just another faraway star. But what if I told you that this unassuming smudge is, in fact, one of the most dangerous and exquisitely beautiful places in the known universe? It's not merely a wisp of gas. The Orion Nebula is a cosmic furnace, a place where stars are born in a blaze of fire, sculpted by immense gravitational forces, and bathed in a torrent of radiation. It is a spectacle of chaos and creation, unfolding right now, a mere 1/300 light-years away from us. Think of it a process so fundamental to the very existence of our Sun, our Earth, and ultimately ourselves, is happening in real time, just a cosmic stone's throw away. If you possessed eyes capable of seeing in the infrared spectrum, a vision far beyond our limited human perception, the fuzzy blur of Orion would transform before you. It would erupt into a landscape of breathtaking vibrancy, revealing the universe in an act of perpetual birth, over and over again. Within this luminous cloud, you would witness secrets, echoes of our own sun's turbulent past, glowing with an inner light. It's a place where the veiled processes of stellar genesis become palpable, an ethereal dance of light and shadow, heat and cold, all playing out in the grand theater of space. So, where exactly is this extraordinary place, this cosmic nursery, and how far do we truly have to journey, both in terms of imagination and the limits of our technology, to truly grasp its essence as you look up at the winter sky? The constellation Orion proudly displays its distinct shape, a mighty hunter with his sword raised, his belt shining with 3 prominent stars. If the night is dark enough, and your eyes are keen, below that shimmering belt, you might catch a glimpse of a small, diffuse patch, appearing to hang from his sword. This is not a single star, or a simple cluster. This is an opening, a window into a galactic masterpiece, the Orion Nebula, also cataloged as Messier 42 or simply M42. It is a dazzling, bright womb of interstellar gas and dust, a birthplace of stars nestled between the vast, silent stretches of the cosmos. Throughout human history, people have gazed upon this particular corner of our Milky Way galaxy, studying it, recording its presence, and weaving countless stories and myths around its ethereal glow. The Orion Nebula is not an isolated island in the cosmic ocean. It is an integral, dynamic part of a much larger structure, the Orion Molecular Cloud Complex. Imagine a colossal stellar nursery, so vast it stretches across hundreds of light years. This immense cloud complex is a cosmic mosaic, incorporating other familiar and equally captivating structures like Barnard's Loop, a sweeping arc of ionized gas, the eerie silhouette of the Horsehead Nebula, and the glowing tendrils of the Flame Nebula. All these celestial wonders are meticulously stitched into the cosmic fabric of Orion's sword, a testament to the intricate interconnectedness of star-forming regions. M42, the object of our current contemplation, is simply the brightest, most intensely active part of this giant, sprawling cosmic entity. What makes M42 even more remarkable is its accessibility. Relatively speaking, even without the aid of a powerful telescope, you can discern its misty blur, a subtle testament to its inherent brilliance. It lies directly in the direction of the Orion Arm, which is itself a minor spiral arm of our Milky Way galaxy. And importantly, it is the very arm where our own solar system quietly resides. This means the Orion Nebula isn't some unfathomably distant realm on the fringes of the cosmos. Instead, it is, in cosmic terms, right in our galactic neighborhood, a spectacularly active region of starbirth unfolding practically on our doorstep. But how far is in our neighborhood really for many years? The precise distance to the Orion Nebula was a subject of considerable debate among astronomers. Initial estimates ranged widely, some placing it as close as 1,500 light-years, others extending its reach beyond 1,800 light-years. However, as our technological prowess has advanced, as our instruments have grown more sophisticated and our observational techniques more refined, we have steadily honed in on a more accurate measurement. With the very latest data, the Orion Nebula is now estimated to be approximately 1,344 light-years away. Give or take a few light-years, if you wanted to express that distance in more familiar, albeit staggering, terrestrial units. That's roughly equivalent to 7.9 quadrillion miles, or about 12.7 quadrillion kilometers. Numbers so vast they humble the imagination, yet incredibly precise in the context of the cosmos. These incredibly precise measurements are not derived from mere guesswork or speculative estimates. They are the result of rigorous scientific methodologies, primarily relying on techniques such as parallax and radio interferometry. Think of parallax this way: close one eye, then the other, and observe an object close to you. Notice how it appears to shift slightly against the distant background. This simple visual phenomenon is the fundamental principle behind astronomical parallax. Scaled up to unimaginable distances, astronomers employ this same principle by observing the Orion Nebula from opposite sides of Earth's orbit around the Sun, a 6-month interval apart, by meticulously measuring the apparent minuscule shift of certain stars within the nebula relative to the unmoving backdrop of much more distant background stars. They can, through straightforward trigonometric calculations, determine the nebula's distance. While immensely powerful, parallax has its limitations, particularly for objects beyond a certain distance, to achieve even greater precision for objects as vast and diffuse as nebulae. Astronomers turn to a technique called Very Long Baseline Interferometry, or VLBI. Imagine a network of multiple radio telescopes, scattered across the surface of Earth, sometimes even extending into space. VLBI is a method that combines the data from all these individual telescopes, effectively transforming them into a single, colossal virtual dish with a diameter equivalent to the maximum separation between the telescopes. This allows for incredibly high angular resolution, making it exceptionally well suited for studying the intricate, spread-out structures of a nebula by integrating VLBI data with observations from space-based telescopes like the Gaia mission, which precisely maps the positions and motions of billions of stars. Scientists have managed to reduce the margin of error for the Orion Nebula's distance to less than 20 light-years on a cosmic scale, where distances are routinely measured in millions or billions of light-years. This level of precision is truly remarkable. As our understanding deepens, things become even stranger, even more fascinating. The Orion Nebula is not a flat, two-dimensional image projected onto the canvas of space. It possesses profound depth within its glowing expanse. There are stars that are tens of light years closer to us, and others that are tens of light years farther away. Imagine gazing into a deeply foggy forest. You perceive layers of trees receding into the distance. Some closer, some further away. The Orion Nebula presents a similar effect, a three-dimensional vista of star formation. Some of the cooler, outer molecular clouds, for instance, are situated at a greater distance from us than the brilliantly glowing trapezium cluster, which forms the nebula's luminous heart. We are not simply looking at the Orion Nebula at a single, fixed distance, but rather looking through a vast, dynamic region of space. And this immense volume, this cosmic laboratory, is intensely alive. The sheer scale of the Orion Nebula is difficult to comprehend. It is truly massive, spanning approximately 24 light-years across, give or take a little. Yet, even this impressive dimension represents only a mere sliver of the full Orion molecular cloud complex, the gigantic stellar nursery of which it is a part. That entire complex stretches for nearly 240 light-years in length. A truly staggering cosmic expanse, what we perceive as the glorious, glowing visible light of M42 is, in essence, just the thin, ionized skin of a much deeper, more voluminous structure. It's as if a giant, cosmic paper lantern is being illuminated from within, its inner workings largely obscured from direct view in visible light, but revealed through other wavelengths, being both relatively close to Earth and incredibly active. M42 has become an indispensable benchmark object for astronomers. Think of it as a kind of galactic Rosetta Stone, a cosmic Rosetta Stone that allows us to decipher the intricate language of stellar birth. It is one of the precious few locations in our galaxy where we can observe and study nearly all phases of stellar formation. From the earliest stages of cold, dense gas collapsing under its own immense gravity, to the dramatic ignition of fiery newborn stars, vigorously burning away their surrounding natal material. And precisely because it is so nearby, our advanced instruments can resolve an unprecedented level of detail at much finer scales than is possible for more distant nebulae, offering us a granular, almost intimate view into these profound cosmic processes. Are you curious about how planetary systems like our own come into being? Orion has them in abundance, in various stages of formation. Do you want to understand how the relentless tide of radiation sculpts and reshapes cosmic matter, influencing the very destinies of emerging worlds? It's all there, unfolding live. A grand celestial experiment playing out before our metaphorical eyes. The proximity of Orion doesn't just offer visual clarity, it also has fascinating implications when we consider the dimension of time. What we are seeing tonight, the glorious light emanating from the Orion Nebula, is light that began its long journey through space around the year 681 AD. That means, in a very real sense, we are looking at a nebula from the 7th century. Imagine that back then, as Earth's diverse societies were rising and falling, as empires emerged and crumbled, as new cultures flourished and old ones faded. The photons that now strike our telescopes were just beginning their epic voyage across the void. We would not know for another 300 years. For instance, if the powerful stars within the trapezium cluster were to go supernova tomorrow, such is the vastness of cosmic timescales, where even events happening now are seen through the lens of a deep, ancient past. So, what exactly is it that makes the Orion Nebula glow with such mesmerizing intensity? What powers those deep reds, those fiery blues, and those eerie greens that seem to paint an oil masterpiece across the night sky? These colors are not merely aesthetically pleasing. They are chemical markers, a language written in light, revealing the very composition and energetic state of the nebula. Why does Orion shine like a colossal lighthouse in the vast cosmic darkness? While most molecular clouds remain hidden, dark and out of sight, visible only by their silhouettes against more distant stars. The answer, at its core, comes down to a fundamental process called ionization, a raw, immensely powerful transformation triggered by the very young, very massive stars nestled within its heart. At the luminous core of the nebula lies the trapezium cluster, a tightly knit group of newly formed stars. These stellar infants have only just ignited the process of nuclear fusion within their scorching cores, beginning their long, bright lives. The brightest and most profoundly influential among them is a star known as Theta 1 Orionis C. This star is nothing short of a cosmic monster. It is dozens of times more massive than our Sun and literally thousands of times more luminous. Its sheer power means it emits an unrelenting, torrential flood of ultraviolet radiation that bathes and permeates the surrounding gas of the nebula. The Orion Nebula is primarily composed of hydrogen gas, the simplest and most abundant element in the entire universe. When the energetic ultraviolet photons streaming from stars like Theta 1 Orionis C collide with hydrogen atoms, they possess enough energy to completely knock electrons off those atoms. This violent interaction transforms neutral hydrogen H into ionized hydrogen H+. Think of it as a continuous, atomic-level lightning storm, a ceaseless electrical discharge on an interstellar scale. These liberated free electrons, however, do not remain separated indefinitely from their positively charged proton counterparts. They eventually find their way back, reconnecting with the protons, and crucially, when they do so, they release photons, bursts of light, at very specific, characteristic wavelengths. These emitted photons collectively form the brilliant, glowing spectrum that we observe from the nebula. This phenomenon is known as recombination radiation, and it is directly responsible for the iconic, pervasive pinkish-red color that so dominates images of the Orion Nebula. More specifically, the most common and intense spectral line observed is called H-alpha, which corresponds to a deep red emission at a precise wavelength of 656.3 nanometers. But hydrogen is not the only element caught in this celestial light storm. Other elements within the nebula's vast gaseous expanse are also energized. For example, oxygen atoms can be energized twice, leading them to glow with a hazy, ethereal greenish-blue hue. Sulfur, when ionized, contributes a darker, reddish tint to the overall palette. Each distinct color observed corresponds to a different element and a specific energy level, making the nebula a cosmic spectrometer. Thus, when scientists look at the Orion Nebula through different filters, they are not merely admiring a light show, they are, in effect, reading its chemical composition and energetic state in real time. Deciphering a complex celestial message, the nebula's glow is not uniform across its entire expanse. The areas that are closest to the powerful trapezium cluster shine with the most intense brilliance. This is precisely where the ultraviolet bombardment is at its peak, creating the highest degree of ionization. As you move outward from the cluster's fiery heart, the intensity of the radiation gradually softens, diminishing its ionizing power. Consequently, the gas in these outer regions begins to transition back to being mostly neutral. This creates a fascinating layered effect, a distinct radiation gradient, where the inner regions are intensely hot and ionized, while the outer zones are progressively cooler and darker. The dynamic boundary separating this hot, ionized gas from the cooler, neutral gas is known as an ionization front. This ionization front is far from a static, unmoving wall. It is a dynamic, evolving boundary that constantly moves, erodes, and reshapes the nebula over vast timescales. The sheer, intense radiation pressure emanating from the central, massive stars within the trapezium cluster is literally blowing away the outer layers of the surrounding gas cloud. In doing so, it slowly but relentlessly reveals the denser, nascent star-forming regions that were previously hidden beneath. In essence, The light of Orion is a dual force. It is both the profound storyteller, revealing the nebula's composition and processes, and the powerful sculptor, constantly molding and refining its intricate shape. The ability to witness this cosmic process actively unfolding before our eyes is truly captivating. Indeed, parts of the Orion Nebula have undergone observable changes within the span of just a few decades, a blink of an eye in astronomical terms. While distant galaxies and faraway quasars evolve over millions or even billions of years, time-lapse images captured by advanced observatories like the Hubble Space Telescope clearly show gas knots shifting, shock fronts spreading, and ionization edges subtly changing shape over timescales that are comprehensible to human observers. This offers an almost unprecedented real-time view of cosmic evolution. However, this very light, this beautiful, life-giving radiation, also carries an element of danger. The same intense ultraviolet light that illuminates the nebula and allows us to perceive its glory can also be detrimental to the delicate process of planet formation. It acts as a powerful eraser, using its light to photo-evaporate the rings of gas and dust that encircle newborn stars, stripping away the very raw materials that could otherwise coalesce into planets. This fascinating, dramatic interplay between creation and destruction, between the forces that give birth to stars and the forces that might stifle planetary systems, is part of what makes the Orion Nebula such a compelling object of study. The light we admire is simultaneously the very force that risks the futures of the nascent systems struggling to form within its embrace. It's also important to note that the Orion Nebula's glow, as perceived by the human eye, is not as intensely bright as the stunning images captured by telescopes might suggest. Our eyes are simply not evolved to clearly discern most of its light, particularly the deep red hydrogen emissions. Most of those breathtaking, vibrant colors you marvel at in professional telescope images are actually captured using techniques involving long exposures and specialized color filters. This doesn't make them fake, rather. They are scientifically accurate translations, revealing wavelengths of light that our visual system was never designed to perceive. If we could somehow tune our vision to match the sensitivity and spectral range of a high-powered astronomical camera, we would undoubtedly see the Orion Nebula as a vast, resplendent stained glass cathedral, lit from within by an eternal, fiery glow. At the absolute heart of this cosmic cathedral, this stellar engine room, lies the trapezium cluster. If we consider the Orion Nebula as a vast, incubating womb for stars, then the trapezium cluster is its pulsating, beating heart, the undeniable source of its life and its chaos. At the very center of the nebula, clustered tightly together, is this group of immensely massive newly formed stars. Their collective heat, their blinding light, and their relentless radiation exert an overwhelming impact on everything you see, and indeed, on much that you don't. Without the searing presence of the trapezium cluster, the Orion Nebula would simply remain a cold, dark, and largely unremarkable cloud of gas. Instead, it has been transformed into a cosmic heater, an incandescent furnace built from the inside out, radiating warmth and energy throughout its vast domain. The cluster derives its name from its distinctive appearance. Its four brightest stars form a rough trapezoidal shape when viewed from Earth. These are specifically identified as Theta, 1 Orionis, A, B, C, and D. These stars are astonishingly young, typically only a few million years old, mere infants in the grand cosmic timescale. However, their youth in no way implies weakness. Quite the opposite. These are O-type and early B-type stars, representing the most massive and energetic stellar classes known to astronomy. Their surface temperatures can soar to over 40,000 Kelvin, making them searing, blue-white beacons of immense power that dominate the sky around them. The single most influential star within this formidable quartet is Theta 1 Orionis C. This star is not merely big, it is monstrously powerful. It is estimated to be approximately 40 times more massive than our Sun, and emits literally thousands of times more energy. This single titanic star is responsible for generating nearly 90% of the ultraviolet radiation that tirelessly ionizes the vast quantities of gas within the nebula. Its stellar wind, a continuous, powerful outflow of charged particles, blasts through the surrounding gas at incredible velocities, reaching speeds of up to 2,000 kilometers per second. This ferocious wind acts as a cosmic sculptor, carving out vast cavities, shaping colossal walls of glowing material, and triggering powerful shock waves that ripple through the surrounding cloud like immense, ongoing detonations. Yet, the trapezium cluster is home to far more than just these four brilliant giants. It is a bustling metropolis of young stars, comprising an estimated over 700 individual young stars, some visible in optical light, many more detectable only in infrared light, hidden within the nebula's dusty folds. Their sizes, their ages, and their activities are incredibly diverse. Some are still encircled by primordial rings of dust, tantalizing hints of early-stage solar systems in the making. Others are already erupting with powerful jets of material and experiencing intense magnetic storms. Collectively, they form one of the densest groups of stars ever observed in the Milky Way, a tightly packed stellar community teeming with activity. What truly defies conventional intuition is the gravitational instability of this entire arrangement. The stars within the trapezium cluster are crammed into an area that spans only about 1.5 light-years across. To put that into perspective, that distance is actually smaller than the distance between our own Sun and Alpha Centauri, our nearest stellar neighbor. Because of their extreme proximity, their immense gravitational fields are in a constant, dynamic interplay, perpetually pulling on each other, subtly altering paths, and sometimes with astonishing force. Ejecting smaller stars from the cluster like slingshots? Indeed, some stars observed as runaways in the broader Orion region may well have originated from this very chaotic core. Violently flung out by gravitational interactions with these massive objects, this chaotic gravitational interaction extends its influence beyond just the stars themselves. It profoundly shapes the nebula in its entirety. The intense, relentless radiation streaming from the trapezium cluster actively blows colossal bubbles into the surrounding gas, creating vast cavities and intricate tunnels. These pathways allow the potent ultraviolet light to escape in focused, directional blasts. These concentrated bursts of radiation are powerful enough to carve out towering pillars of gas and dust, create bright, illuminated rims around denser regions, and even trigger new waves of star formation when they compress nearby gas clouds to critical densities. It's the ultimate feedback loop in action. The very stars being born are actively shaping the environment, an environment that, in turn, facilitates the birth of even more stars. Another fascinating aspect of the trapezium cluster is its role in mass segregation. This is a process where the heaviest stars in a cluster tend to migrate towards the center over time, while smaller stars are progressively pushed towards the periphery. In the case of the trapezium cluster, this phenomenon appears to have occurred remarkably quickly, perhaps even before the cluster had fully coalesced. While it's still an active area of research, whether this rapid mass segregation is due to post-formation gravitational dynamics or to the very initial conditions of the cluster's birth, the result is unequivocally clear. The most massive and luminous stars are tightly packed into the core, reigning supreme over this stellar nursery and directly influencing the birth of new stars. Even more intriguing are the protostellar rings, or proplids, that encircle some of the stars both within and immediately around the trapezium cluster. These proplids are the literal building blocks of future solar systems, and the trapezium's fierce radiation is actively forming them, eroding them, and, in some cases, blasting right through them. High-resolution images reveal teardrop-shaped shadows trailing these disks, appearing like cosmic capes caught in a relentless stellar wind. It's a breathtaking tableau of simultaneous beauty and violence. The trapezium cluster serves as an unparalleled laboratory, offering a compressed, intensified view of what happens when stars attempt to form too quickly and too closely to one another under incredibly harsh, energetic conditions. Every subtle spark, every propagating wave, every infrared flash provides a new piece of information. Another crucial hint about how our own sun might have come into being, born amidst chaos, alongside giants, within the blazing light of something far grander than itself. To truly begin to comprehend the Orion Nebula, do not start with its mesmerizing colors. Instead, begin with the trapezium. That is the brain, the heater, the beast, orchestrating all the dazzling noise. Now, let us turn our gaze to those faint, ethereal structures. The cosmic ink drops suspended in the fiery air, little shadows wreathed in the edges of a brilliant glow, the proplyds, or protoplanetary disks. These are the solar systems in the making, still in their cosmic wombs, and we are witnessing their very formation in the Orion Nebula. Not just generally, not theoretically, but in real time, captured by cameras sharp enough to pierce through vast clouds of dust and the blinding light of emergent stars. Each proplyd is a very young star, often less than 1 million years old, still swaddled in a rotating disk of gas and dust. It is a celestial nursery, surrounded by the raw, fundamental materials of creation: hydrogen, helium, various carbon compounds, microscopic ice grains, and silicates, the ingredients that will eventually form rocks, metals, and water over the immense spans of cosmic time, if such a disk survives long enough. The tiny particles within it begin a slow, gentle dance of accretion. First, microscopic grains stick together. Then they grow into pebbles, which gradually coalesce into mountain-sized planetesimals. Eventually, given enough time and undisturbed growth, these nascent building blocks can evolve into full-fledged planets, orbiting a central star, much like our own solar system. This, however, describes the ideal, textbook scenario for planet formation, a serene and undisturbed process. In the Orion Nebula, the reality is far more challenging, far more dramatic. Here, things are much tougher, much more brutal than they appear. These proplyds are not forming in some peaceful, isolated corner of space. They are emerging, literally, within the blast zone of the trapezium cluster, constantly bombarded by the intense, sterilizing ultraviolet light streaming from colossal stars like Theta 1 Orionis C. This relentless radiation acts like a cosmic vacuum cleaner, stripping the gas from these forming disks, heating it to thousands of degrees, and forcefully blowing it off into space in long, trailing flows. Indeed, many of the proplyds observed in Orion possess distinct tails, reminiscent of comets. This is a direct visual testament to the radiation literally peeling back the outer layers of the disk, vaporizing its precious raw materials. This makes the Orion Nebula a place of stark contrast. It is both a vibrant birthplace and a brutal battlefield. These nascent planetary systems are engaged in a desperate race against time, desperately trying to gather enough dust and gas to collapse into planets before their essential raw materials are utterly destroyed by the very stars that illuminate the nebula with such breathtaking beauty. It's the cosmic equivalent of attempting to build a house during a ferocious sandstorm, with a flamethrower simultaneously aimed at your blueprints. Yet, despite this profound destruction, life, in the cosmic sense, finds a way. Dozens, perhaps even hundreds, of proplyds have been identified in Orion. Some appear to be tightly packed and thick, their disks showing minimal signs of erosion, suggesting they might still have a good chance of forming planets. Others, however, are already visibly thinner, indicating that much of their planet-forming material has been stripped away, leaving less for the creation of new worlds. Their ability to survive, to persist against the onslaught, seems to be directly correlated with their proximity to the trapezium cluster. The closer they are to its powerful, radiating heart, the stronger the destructive radiation, and consequently, the shorter their potential lifespan. Some proplids are even observed to be surrounded by bow shocks, dramatic arc-shaped structures formed when the ferocious stellar wind from the central star slams directly into the surrounding ionized gas, creating a visible compression. These bow shocks serve as stark markers of the intense boundaries of stellar influence, starkly hinting at the sheer quantities of energy being violently thrown around in this chaotic nursery. It's akin to observing the complex, destructive interactions of 1,000 hurricanes, each possessing its own gravitational pull, its own rotational spin, and its own searing heat. Thanks to the incredible capabilities of the Hubble Space Telescope, and more recently, the even more powerful James Webb Space Telescope JWST, astronomers have been able to peer deeper into the intricate structures of these proplids than ever before. In some, they have observed tantalizing gaps and rings within the dusty disks, tantalizing early signs of ongoing planet formation. These subtle features echo the structures we see in older, more evolved disks, such as those around stars in the Taurus star-forming region, or the famous image of HL Tauri. Orion, however, offers us a younger, far more chaotic version of these processes, providing a unique glimpse into what may have transpired before systems like our own even began to settle into their familiar, structured forms. These observations, these tantalizing hypotheses, are not merely pretty pictures for our enjoyment. They are profound hints about our own cosmic origins. It is entirely plausible that our own solar system may have begun its existence in a place very much like the Orion Nebula, where it was bathed in intense radiation, where it formed in close proximity to massive destructive stars, and where its primordial protoplanetary disk struggled fiercely to remain intact. There is even compelling evidence, derived from meteorites found on Earth, suggesting that debris from a nearby supernova event may have been incorporated into our early solar nebula. This implies that, much like the proplids we observe in Orion, we too were born in a chaotic, intensely active, and perhaps even violently clumpy stellar neighborhood. Therefore, when we study the proplids of Orion, we are not just contemplating the potential futures of other systems, we are actively helping to decipher the profound mysteries of our own deep past. Another intriguing possibility, a slightly darker fate for some of these cosmic embryos, is that they might not form planets at all. If they lose too much material too quickly due to the radiation, they may never accumulate enough mass to ignite nuclear fusion and become a star. Instead, they might collapse into brown dwarfs or very low-mass stars, an entirely different evolutionary path still profoundly shaped by the violence of their birthplace. Others might eventually birth rogue planets, worlds violently ejected from their nascent systems during turbulent gravitational interactions, forever doomed to drift through the vast interstellar medium of the galaxy, alone and without the comforting warmth of a sun. Each bright bead in Orion, each faint, dusty disk, holds its own unique story, its own unfolding destiny. Some are valiantly holding on. A few are inevitably breaking apart. Some may already harbor colossal, forming worlds, perhaps even giant gas planets like Jupiter, taking shape deep within their protective dusty rings. We do not yet know the ultimate fate of each individual proplid, but we can, with our increasingly keen instruments, bear witness to their ongoing struggle, their dramatic fight for existence. One of the most amazing privileges of modern astronomy is that it allows us to observe, in staggering detail, how planetary systems are assembled in the very first, chaotic moments of their formation. Moving deeper into the Orion Nebula, we encounter a fascinating class of objects that often blur the very lines of cosmic classification, the brown dwarfs. These are abundant in Orion, representing a realm where celestial bodies attempt to become stars, almost make it, but ultimately fall just short of igniting the sustained nuclear fusion that defines a true star. Brown dwarfs are precisely these kinds of objects, and the Orion Nebula is teeming with them. Often, brown dwarfs are colloquially referred to as failed stars. However, this seemingly dismissive nickname truly doesn't do justice to their intrinsic strangeness and the unique, hybrid nature of these cosmic entities. They are not quite stars, primarily because they do not possess sufficient mass, typically less than 0.08 times the mass of our Sun, to sustain the hydrogen fusion reactions that power our Sun and other main sequence stars, allowing them to shine brightly for billions of years. But simultaneously, they are also not planets, because they form through the same fundamental process as stars, the gravitational collapse of gas and dust within a nebula. This places them in a peculiar cosmic identity crisis. They are too large to be classified as planets, yet too small to shine with the sustained brilliance of a star. In the active, turbulent environment of the Orion Nebula, brown dwarfs are surprisingly common, thanks to extensive infrared surveys and high-resolution imaging from powerful telescopes like Hubble, Spitzer, and most recently, the revolutionary JWST. Astronomers have been able to identify dozens, perhaps even hundreds. Of these enigmatic objects, they often lurk, almost unnoticed, within the dusty folds of M42 like smaller siblings in the background, easily overlooked without the specialized infrared eyes of these advanced instruments. Many of these brown dwarfs are exceptionally young, some perhaps only a few million years old. This youth makes Orion an unparalleled laboratory for studying how brown dwarfs form, how they evolve over time, and what their early lives entail. Unlike the older, cooler brown dwarfs that drift quietly through the vast emptiness of the galaxy, those in Orion are still warm from their tumultuous birth, providing invaluable clues to their origins. Intriguingly, like true stars, some of these young brown dwarfs are observed to be surrounded by their own rings of dust and gas. Much like the proplids we discussed earlier, this tantalizing discovery opens up the exciting possibility that brown dwarfs, despite their dim nature, could potentially host their own miniature planetary systems, albeit ones that would be significantly smaller and much, much cooler than our own. But how do these peculiar objects actually come into being? That is where the cosmic plot thickens, where certainty gives way to intriguing possibilities. One prevailing idea posits that brown dwarfs form in precisely the same manner as stars from the gravitational collapse of gas clouds. The only difference is that these particular clouds simply never accumulate enough mass to reach the critical threshold for sustained nuclear fusion. They just fall short. Another compelling hypothesis suggests a more dramatic origin, that brown dwarfs were once part of larger, developing stellar systems but were violently ejected from those systems due to powerful gravitational interactions. This scenario is akin to a smaller, less fortunate participant being unceremoniously thrown out of a crowded, chaotic theater. Such a violent ejection could help explain why some brown dwarfs appear to drift alone, isolated in space, while others remain in relatively close proximity to groups of stars. In the dynamic environment of the Orion Nebula, we observe evidence that supports both of these intriguing scenarios. Some brown dwarfs are found deeply embedded in the densest parts of the cloud, still surrounded by gas and potentially still accreting material. Consistent with the direct collapse model, others are seen drifting solo, far from the bustling action of the star-forming regions, as if they were indeed flung out during a colossal cosmic scuffle. The incredibly chaotic gravitational soup of the trapezium cluster, with its tightly packed, massive stars, could easily impart enough energy to toss a low-mass object across many light-years of space. Even more challenging to our existing classifications are some objects in Orion whose masses fall below the traditional brown dwarf threshold, dipping to as low as a few times the mass of Jupiter. Yet, these objects still show clear evidence of having their own disks of gas and dust, and possibly even forming moons or microplanets around them. These extreme objects fundamentally challenge our very definitions of planet and star. Are they truly rogue planets? Wandering aimlessly without a parent star, are they sub-brown dwarfs, a new, even lighter class of celestial body? Or are they simply planetary embryos that failed to find a stellar parent, whatever their ultimate classification? They do not fit neatly into any existing category, underscoring that Orion is a fertile breeding ground for cosmic rule breakers. Observing brown dwarfs directly is notoriously difficult due to their lack of significant visible light emission. The most effective way to detect and study them is through infrared astronomy. Where they're faint, residual heat glows slightly. Some brown dwarfs even exhibit unexpected flares and emit X-rays, providing tantalizing evidence that their magnetic activity can, in some ways, mirror that of much larger, more powerful stars. They are not merely inert balls of gas, they are living, evolving entities, dynamic and changing, existing at the very edges of our understanding of stellar physics. And here's a truly surprising fact, though: they may be dim. Brown dwarfs might be numerically dominant in regions like Orion. That's right. It is entirely possible that there are more brown dwarfs than actual stars in some active star-forming regions, while they contribute far less light or heat to the overall cosmic budget. They add significantly to the total mass. They fill in the gaps, subtly shaping the gravitational environment of the cluster. They are, in essence, the quiet cosmic majority. So, why do these enigmatic brown dwarfs matter so profoundly to our understanding of the universe? Because they blur the traditional line between what we define as a planet and what we define as a star. This makes them crucial to our comprehensive understanding of how everything, from tiny planets to colossal stars, ultimately forms. Are they merely an accidental byproduct of clustered star formation? Or are they a natural, inevitable consequence? Do all nebulae produce them in such abundance? Or is Orion an unusually rich nursery for these substellar objects? And most tantalizingly, if these substellar objects can host their own planets or moons, could they quietly, unnoticed, harbor life in dark, frozen systems? Existing in a realm far beyond our conventional search for habitable worlds, the Orion Nebula does not easily reveal its profound secrets. But every brown dwarf we discover, every faint infrared glow detected in its depths, represents a new clue, another piece in the grand puzzle of cosmic formation. It's a testament to the immense range of outcomes that can occur when gas collapses under its own weight, demonstrating that not every cloud is destined to ignite into a sun. And, perhaps most poetically, not becoming a sun does not mean becoming nothing. Let's now consider the very fabric of the Orion Nebula itself, and the turbulent, chaotic environment within it that serves as the crucible for starbirth. Stars do not form in a slow, gentle, or predictable manner. The process within the Orion Nebula is rough, profoundly unpredictable, and exceptionally difficult to control or fully anticipate. Discard any mental image you might hold of beautiful, serene pictures depicting stars slowly condensing and peaceful, dark cocoons of gas. This place is far more akin to a cosmic riot, a spectacular, unceasing clash of light, wind, gravity, magnetic fields, and shock waves, all unfolding simultaneously. It's the galaxy itself in constant, churning motion, and this motion, this relentless turbulence, is not merely background noise, it is an utterly integral, fundamental part of how stars are created. The Orion Nebula is, in essence, a living, breathing textbook example of turbulent star formation. Here, supersonic flows of gas smash violently into each other, compress under immense gravitational forces, and twist into complex spirals around embryonic stars. These flows are not tranquil, laminar streams, they are explosive shock waves, powerful jet streams of material, and swirling magnetic cyclones. Each component moves at astonishing speeds, ranging from tens to hundreds of kilometers per second. To visualize this, you are effectively looking at an interstellar tempest, something far grander and more violent than a terrestrial hurricane, yet with the explosive power and suddenness of a continuous detonation, unfolding across dozens of light years. Where does all this profound chaos originate? It all begins with gravity. As thick, dense regions of molecular gas within the nebula begin to collapse under their own immense weight, they inevitably pull in even more surrounding matter, accelerating the inward fall. But this infalling gas does not simply settle gently onto the forming core. Instead, it slams, it crashes, it breaks apart. As the stellar core begins to form, the infalling pieces twist and turn around it, adding to the chaotic dance. In a perfectly smooth, idealized, and theoretical universe, this entire process might occur with elegant, predictable neatness. However, Orion is far from perfect. It is, by cosmic standards, a magnificent mess. The incoming gas streams originate from multiple directions, leading to a cacophony of collisions and compressions, each exerting different forces. Adding to this inherent turbulence are the powerful stellar winds emanating from the massive stars within clusters like the trapezium. These winds are not gentle breezes, they are ferocious bursts of charged particles, speeding through the nebula at velocities far exceeding the speed of sound. Injecting incredible amounts of kinetic energy and carving out vast holes in the gas, they tear through the nebula, sowing chaos wherever they go, much like a fleet of jet engines ripping through a thick fog bank. The result of these combined forces is the creation of complex shear zones, swirling eddies, and distinct clumpy structures where gas rapidly builds up before collapsing again. And the chaos isn't purely physical motion. There's a profound, often invisible, layer of magnetism intricately interwoven into this turbulent environment. The Orion Nebula is extensively threaded with magnetic fields. These fields, though unseen, are incredibly powerful. They resist the gravitational collapse of gas in certain directions, subtly slowing down some flows while channeling others along specific pathways. They act like an unseen scaffolding, or perhaps cosmic tension wires, guiding and restraining the tumultuous gas. But even magnetic fields, under extreme pressure, can buckle and contort, adding yet another layer of stress and complexity to an already explosive environment. This intricate interplay of gravity, gas dynamics, and magnetic fields is precisely why star formation in Orion is both incredibly efficient and profoundly chaotic. On one hand, you have these rapidly collapsing cores efficiently forming stars, some in as little as 100,000 years and an absolute blink of an eye in cosmic time. On the other hand, you have vast quantities of material being violently blasted apart, evaporated, and jostled out of gravitational equilibrium. It's a relentless feedback loop of destruction enabling creation. Each powerful shock front can either trigger a new gravitational collapse, igniting a nascent star, or it can disperse a potential stellar embryo entirely, preventing its formation. Astronomers meticulously study these turbulent flows using both detailed imaging and sophisticated spectroscopy. By carefully analyzing how light from different parts of the nebula is shifted and broadened, they can create a detailed map of the gas's speed and direction. What they discover is often astonishing. The speeds vary wildly from one area to the next. Some gas is rushing towards us. Some is receding away. Some of it is caught in tight, energetic twists, while other portions are propelled in long, straight-line flows. The nebula, in its entirety, is a three-dimensional jumble of disordered motion, a cosmic maelstrom where speeds fluctuate dramatically. And yet, amidst this apparent chaos, remarkable patterns emerge in the densest regions of turbulence. You will frequently find the very youngest stars, still in their earliest embryonic stages. Why? Because these are the precise locations where chaotic pressure builds up to critical levels, forcing the gas to collapse. It's like twisting a balloon tighter and tighter until a bulge inevitably forms. Eventually, it has to give way. These extreme pressure points create incredibly dense clumps of gas that rapidly form protostars. In a profound way, turbulence acts as both the antagonist and the matchmaker of star formation. It vigorously resists easy, uniform collapse. But when it does finally allow collapse to occur, the result is explosive and incredibly efficient. This is the fundamental reason why stars do not form evenly across the vast expanse of the Orion molecular cloud. Instead, they coalesce in distinct groups, patches, and elongated strands, precisely in those localized areas where the turbulent flows of gas converged and intertwined just right. It is highly likely that some stars even form in long, intricate strings, tracing the paths of powerful shock fronts or invisible magnetic waveguides. So, while it appears wild and unbridled, the chaos of Orion is far from random. Understanding this intricate managed chaos is not merely an academic exercise. It has profound implications for every aspect of star formation, from determining the ultimate size of newly formed stars to influencing whether planetary systems can subsequently form around them. If there is too much disturbance, the delicate gas within a forming disk might never settle sufficiently to coalesce into planets. Conversely, if the turbulent forces are not strong enough, the cloud might fall apart too slowly to keep pace with the powerful. Destructive radiation from nearby. Massive stars. The Goldilocks zone for star creation isn't just about the right amount of heat or mass. It's also about the optimal level of managed chaos. In the Orion Nebula, we are granted an unparalleled, high-clarity view of this cosmic confusion. The ethereal wisps of light that resemble abstract art are actually strands of shocked gas, tearing through the nebula faster than the speed of sound. The arc-like shapes and ripples we observe are the powerful blast waves from newly ignited stars, or the dynamic results of converging gas flows. It's not just gas. It's the raw material for stars that have valiantly survived the tumultuous fight for existence. Now, let's explore another peculiar, yet fundamental phenomenon occurring at the heart of the Orion Nebula mass segregation. This is why the biggest stars cluster so densely at the very center. There is a strikingly unusual event unfolding at the core of the Orion Nebula. The most massive stars within the trapezium cluster are not distributed randomly throughout the region. Instead, they are all tightly huddled together, forming a concentrated core, almost like important figures gathered in the eye of a cosmic storm. Surrounding them are hundreds of tiny stars, a multitude of brown dwarfs, and countless disks that are actively forming planets. This arrangement is no accident. This profound spatial phenomenon in the cosmos is known as mass segregation, and it is observed with stunning clarity in Orion. But what exactly does mass segregation truly mean? Mass segregation is the dynamic process by which heavier, more massive stars tend to migrate or sink towards the center of a star cluster over vast timescales, while their smaller, lighter stellar siblings are progressively pushed or kicked away towards the cluster's outer edges. This occurs primarily due to gravitational interactions, which can be thought of as a kind of cosmic billiards game. Heavier stars, with their greater gravitational pull and often slower inherent velocities, naturally settle deeper into the cluster's gravitational well, much like denser objects sinking to the bottom of a fluid. Conversely, lighter stars, with less gravitational pull and often higher velocities, are more likely to be flung or drift towards the periphery. It's akin to shaking a jar filled with both sand and rocks, eventually. The larger, heavier rocks will settle towards the bottom, while the sand remains more dispersed. In the case of the Orion Nebula, this settling or segregation appears to have happened remarkably early in the cluster's life, perhaps even before the cluster was fully formed and stable. In fact, some astronomers propose that the mass segregation we vividly observe in Orion today is primordial. This means that the massive stars were not born elsewhere and then migrated to the center. Rather, they emerged right in the very heart of the action, already concentrated near the deepest gravitational potentials. Why is this significant? Because it fundamentally challenges and reshapes our traditional understanding of how star clusters evolve. If mass segregation is inherently built in from the very beginning, it strongly suggests that massive stars only form under very specific, highly dense central conditions, precisely in those deepest wells of gravitational potential within a collapsing gas cloud. It implies that the core of a forming stellar nursery may be pre-programmed to give birth to these colossal giants from the outset. And what magnificent giants they are! Theta 1 Orionis C, the undisputed dominant star of the trapezium cluster. With its mass approximately 40 times that of our Sun and emitting thousands of times more energy, alongside other massive O and B-type stars nearby, completely redefines and reshapes their immediate environment. Their very existence generates ferocious ultraviolet radiation, powerful stellar winds, and intense magnetic chaos throughout the surrounding nebula. In doing so, these giants both fuel and suppress further star formation because they form first and sink deepest into the gravitational well. These are also the very stars most likely to dramatically alter or even destroy their surroundings by vigorously blowing away gas, violently disrupting nascent planetary disks, and intensely heating the entire region. We can clearly observe how this profound influence plays out in Orion. The entire cloud is visibly flattened, intensely electrified, and fragmented around the trapezium cluster. These cosmic scars are the direct result of the immense radiation pressure exerted by these central giants. But why does this division, this segregation by mass, occur in the first place? One idea is based purely on dynamics. As the cluster grows and its constituent stars dynamically interact with each other, the heavier ones tend to lose kinetic energy through close encounters and naturally move closer together. Like balls falling into a gravitational pool at the center. However, the Orion Nebula, being relatively young, estimated to be only 1 to 2 million years old, may not have had sufficient time for this purely dynamic process to fully complete. This is why many astronomers lean towards the hypothesis that the nebula's initial conditions, the very way the gas cloud collapsed and formed, inherently pushed most of its mass towards the center from the beginning. Another compelling idea is tied to competitive accretion. In this model, protostars that happen to be located in the dense central regions of a collapsing gas cloud have significantly more immediate access to the continuous flow of infalling material. They grow larger and accrete mass much faster, essentially feeding from the environment like cosmic parasites with front-row seats at a celestial buffet. Stars at the periphery, by contrast, have access to less material and thus experience slower growth. This inherent natural imbalance leads to the massive stars forming first in the core and quickly locking in their gravitational dominance. Their immense gravity can then actively disrupt the orbits of nearby smaller stars, sending them into elongated, chaotic paths, or even violently ejecting smaller objects entirely, transforming them into runaway stars or isolated brown dwarfs. In this sense, the mass segregation observed in Orion isn't just a static arrangement of stars. It's a dynamic, actively evolving system where the center wields immense power, and the edges keenly feel the profound consequences of that central dominance. This clustering of massive objects has tangible, far-reaching effects. It significantly alters the lifespan of the nebula itself. Because massive stars, by their very nature, burn through their fuel much more quickly and die young, often in spectacular supernovae that can literally tear the surrounding area apart. The intense radiation from these central dominant stars can also photoevaporate protoplanetary disks, fundamentally changing the very likelihood and nature of planet formation around their less massive siblings. Furthermore, it profoundly changes the overall form and structure of the entire cloud. The interplay of overwhelming gravity and the fierce feedback from these giants carves out vast holes, delicate strands, powerful radiation walls, intricate filaments, and towering pillars, a magnificent cosmic sculpture. Painstakingly carved by the relentless force of radiation, it appears there might be a slight misunderstanding. We just finished Chapter 1 and we're about to proceed with Chapter 2 based on the outline. The previous instruction was to say, Tiep tuk chuang chuang 2 if you were ready. I am ready to continue writing Chapter 2, following the detailed outline we established. Please confirm if you would like me to proceed with Chapter 2 now, as our thoughts gently drift through the cosmic tapestry of Orion. Let's allow our minds to settle on the very nature of light itself. What truly makes the Orion Nebula blaze with such captivating intensity? What power paints those deep, resonant reds, those fierce, almost otherworldly blues, and those eerie, luminous greens across the vast canvas of the night sky? These colors are not merely a feast for our eyes, a spectacular cosmic art show. No, they are something far more profound. They are chemical markers, a silent, intricate language written in pure light, revealing the very essence of the nebula. Have you ever wondered why Orion shines like a colossal lighthouse guiding ships across an endless, dark sea? While most other molecular clouds, those vast reservoirs of cosmic gas and dust, remain veiled, hidden from our sight, visible only as ghostly silhouettes against the distant stars. The answer, at its very core, lies in a fundamental, raw, and immensely powerful process called ionization. It is a transformation triggered by the very young, unimaginably massive stars that reside at the heart of this cosmic marvel. Imagine, for a moment, journeying to the luminous core of the nebula. Here, nestled tightly together, you would find the trapezium cluster, a vibrant, tumultuous nursery where stars have only just begun their fiery lives. These stellar infants have recently ignited the process of nuclear fusion within their scorching hearts, converting hydrogen into helium and releasing an unimaginable torrent of energy. Among them, one star stands out, a true behemoth that casts its colossal shadow over the entire nebula, Theta 1 Orionis C. This star is not merely large, it is a cosmic monster, dwarfing our own sun by dozens of times in mass and outshining it by thousands of times in luminosity. Its sheer power unleashes an unrelenting, torrential flood of ultraviolet radiation, a silent, invisible river of energy that bathes and permeates every corner of the surrounding gas. The Orion Nebula is primarily composed of hydrogen gas, the simplest and most abundant element in the entire universe. It's the foundational building block of everything we see. When the highly energetic ultraviolet photons, streaming from stars like Theta 1 Orionis C, collide with these unassuming hydrogen atoms, they carry so much energy that they literally knock electrons completely off those atoms. It's a violent, atomic-level interaction, stripping the atom bare. This transformative process converts neutral hydrogen H into ionized hydrogen H+, a state where the atom has lost its electron and is now electrically charged. Think of it as a continuous, gentle lightning storm, an unceasing electrical discharge playing out on a grand, interstellar scale, lighting up the void. These liberated, free electrons, once separated from their parent atoms, do not remain adrift indefinitely. They are drawn back by the positive charge of the protons they left behind. Eventually, inevitably, they find their way back, reconnecting with those positively charged protons. And this is the crucial moment, the point where the magic of light truly happens. When an electron recombines with a proton, it releases energy in the form of photons, tiny packets of light at very specific, characteristic wavelengths. These emitted photons collectively form the brilliant, glowing spectrum that we observe emanating from the nebula. This breathtaking phenomenon is known as recombination radiation, and it is directly responsible for the iconic, pervasive pinkish-red color that dominates so many of the stunning images of the Orion Nebula we see. More precisely, the most common and intense spectral line observed from this process is called H-alpha, which corresponds to a deep red emission at a very precise wavelength of 656.3 nanometers. It's like the universe is painting with specific colors, each representing a unique interaction. But hydrogen is not the only element caught in this glorious celestial light storm. Other elements present within the nebula's vast gaseous expanse are also energized by the relentless ultraviolet assault. For example, oxygen atoms can be excited and energized twice, causing them to glow with a hazy, almost ethereal greenish-blue hue. Sulfur, when similarly ionized, contributes a slightly darker, more muted reddish tint to the overall cosmic palette. Each distinct color we observe corresponds to a different element and a very specific energy level, making the nebula itself a gigantic, natural spectrometer. Thus, when scientists meticulously gaze at the Orion Nebula through various filters, they are not merely admiring a beautiful, abstract light show, they are, in essence, reading its chemical composition and its energetic state in real time, deciphering a complex, ongoing celestial message whispered across the light years. It's like decoding an ancient scroll written in starlight. The nebula's luminous glow is not, however, uniform across its entire immense expanse. Imagine a powerful spotlight shining in a dark room, the areas closest to the powerful trapezium cluster, the heart of the light, shine with the most intense brilliance. This is precisely where the ultraviolet bombardment is at its peak, creating the highest degree of ionization, the most vibrant reactions. As you gradually move outward from the cluster's fiery core, the intensity of the radiation subtly softens, its ionizing power diminishing with distance. Consequently, the gas in these outer regions begins to transition back to being mostly neutral, less excited, less luminous. This dynamic interplay creates a fascinating layered effect, a distinct radiation gradient, where the inner regions are intensely hot and highly ionized, while the outer zones are progressively cooler and darker, gently fading into the surrounding void, the dynamic boundary separating this hot, ionized gas from the cooler. Neutral gas is a crucial feature known as an ionization front. This ionization front is far from a static, unmoving wall. Think of it more as a living, breathing, evolving boundary that constantly moves, slowly erodes the surrounding gas, and dramatically reshapes the nebula over vast timescales. The sheer, intense radiation pressure emanating from the central, massive stars within the trapezium cluster is, quite literally, blowing away the outer layers of the surrounding gas cloud. In doing so, it slowly but relentlessly reveals the denser, nascent star-forming regions that were previously hidden, shrouded beneath the veils of gas and dust. In essence, the light of Orion serves a dual, profound purpose. It is both the eloquent storyteller, revealing the nebula's intricate composition and the processes unfolding within it, and the powerful sculptor, constantly molding and refining its intricate, ever-changing shape. The ability to witness this profound cosmic process actively unfolding before our very eyes is truly captivating. A dance of creation and destruction. Indeed, parts of the Orion Nebula have undergone noticeable, observable changes within the relatively short span of just a few decades, a mere blink of an eye in the grand, leisurely march of astronomical time, while distant galaxies and faraway quasars evolve over millions or even billions of years. Time-lapse images meticulously captured by advanced observatories like the Hubble Space Telescope clearly show gas knots subtly shifting, powerful shock fronts spreading across vast distances, and ionization edges gently, yet perceptibly, changing their shape over timescales that are remarkably comprehensible to human observers. This offers us an almost unprecedented real-time view into the subtle, yet powerful, forces of cosmic evolution. However, it's a truth that this very light, this beautiful, seemingly life-giving radiation, also carries an inherent element of danger. The same intense ultraviolet light that so brilliantly illuminates the nebula and allows us to perceive its glory can also be profoundly detrimental to the delicate, nascent process of planet formation. It acts like a powerful cosmic eraser, using its light to photoevaporate the rings of gas and dust that majestically encircle newborn stars, stripping away the very raw materials that could otherwise gently coalesce and form into planets. This fascinating, dramatic interplay between creation and destruction, between the forces that give birth to stars and the forces that might stifle the emergence of entire planetary systems, is a central theme. Part of what makes the Orion Nebula such an endlessly compelling object of study, the light we so admire, the light that draws our gaze, is simultaneously the very force that risks the fragile futures of the nascent systems struggling to form within its incandescent embrace. It's also a quiet truth, a gentle reminder of our human limitations, that the Orion Nebula's glow, as it would be perceived by the unaided human eye, is not as intensely bright or as vibrantly colorful as the stunning, awe-inspiring images captured by powerful telescopes might suggest. Our eyes, remarkable as they are simply not evolved to clearly discern most of its light, particularly the deep, elusive red hydrogen emissions, most of those breathtaking, vibrant colors you marvel at in professional telescope images are actually captured using highly specialized techniques involving long exposures and precise color filters. This doesn't make them fake, not in the slightest. Rather, they are scientifically accurate translations, revealing wavelengths of light that our everyday visual system was simply never designed to perceive. If we could somehow tune our vision, recalibrate our eyes to match the exquisite sensitivity and broad spectral range of a high-powered astronomical camera, we would undoubtedly witness the Orion Nebula not as a faint smudge, but as a vast, resplendent, stained glass cathedral, perpetually lit from within by an eternal, fiery glow. A true cosmic masterpiece, at the absolute pulsing heart of this cosmic cathedral, this dynamic stellar engine room, lies the trapezium cluster. If we choose to imagine the Orion Nebula as a vast, incubating womb for stars, then the trapezium cluster is undeniably its pulsating, beating heart, the undeniable source of its life, its light, and its magnificent chaos. At the very center of the nebula, clustered tightly together, is this group of immensely massive, newly formed stars, their collective heat, their blinding, overwhelming light, and their relentless, energetic radiation exert an overwhelming impact on literally everything you see, and indeed, on much that you don't yet perceive. Without the searing, luminous presence of the trapezium cluster, the Orion Nebula would simply remain a cold, dark, and largely unremarkable cloud of gas, indistinguishable from countless others. Instead, it has been transformed, utterly and completely, into a colossal cosmic heater, an incandescent furnace built from the inside out, tirelessly radiating warmth and energy throughout its vast domain, bringing life to the surrounding gas. The cluster derives its evocative name from its distinctive appearance. Its four brightest stars form a rough, almost perfect trapezoidal shape when viewed from Earth. Hence the name. These stars are specifically identified by astronomers as Theta 1 Orionis A, B, C, and D. These stars are astonishingly young, typically estimated to be only a few million years old, mere infants in the grand, unhurried march of the cosmic timescale. However, their youth in no way implies weakness or fragility. Quite the opposite. In fact, these are classified as O-type and early B-type stars, representing the very most massive and energetically powerful stellar classes known to astronomy. Their surface temperatures can soar to truly blistering levels, exceeding 40,000 Kelvin, making them searing. Blue-white beacons of immense power that utterly dominate the immediate sky around them. Their brilliance is almost painful to imagine. Among this formidable quartet, the single most influential star, the true titan of the cluster, is Theta 1 Orionis C. This star is not merely large, it is, in every sense of the word, monstrously powerful. It is estimated to be approximately 40 times more massive than our Sun, and it emits an incomprehensible amount of energy, shining literally thousands of times more luminously. This single titanic star is solely responsible for generating nearly 90% of the ultraviolet radiation that tirelessly ionizes the vast quantities of gas within the nebula. Driving the entire luminous spectacle we witness, its stellar wind, a continuous, powerful outflow of charged particles, blasts through the surrounding gas at utterly incredible velocities, reaching speeds of up to 2,000 kilometers per second. This ferocious wind acts as a relentless cosmic sculptor, carving out vast, intricate cavities within the gas, shaping colossal walls of glowing material, and triggering powerful shock waves that ripple through the surrounding cloud like immense, ongoing detonations, each one a testament to its raw power. Yet, the trapezium cluster is home to far more than just these four brilliant giants. It is a bustling, vibrant metropolis of young stars, comprising an estimated over 700 individual young stars. A teeming community. Some of these can be glimpsed with visible light telescopes, but many more are detectable only in infrared light, cunningly hidden within the nebula's thick, dusty folds. Their sizes, their individual ages, and their activities are incredibly diverse. A spectrum of stellar life. Some are still delicately encircled by primordial rings of dust. Tantalizing hints of early-stage solar systems patiently taking shape. Others are already erupting with powerful jets of material, violent outflows, and experiencing intense magnetic storms on their surfaces. Collectively, they form one of the densest groups of stars ever observed in the entire Milky Way galaxy. A tightly packed stellar community teeming with an almost unimaginable level of activity. What truly defies our conventional intuition, what seems almost impossible, is the inherent gravitational instability of this entire arrangement. The stars within the trapezium cluster are crammed into an area that spans only about 1.5 light-years across. To truly grasp this scale, consider that distance is actually smaller than the distance between our own Sun and Alpha Centauri, our nearest stellar neighbor. Because of their extreme proximity, their immense gravitational fields are locked in a constant, dynamic interplay, perpetually pulling on each other, subtly altering paths, and sometimes, with astonishing brutal force, ejecting smaller stars from the cluster like slingshots, firing pebbles across the void. Indeed, some stars observed as runaways in the broader Orion region, seemingly adrift and isolated, may very well have originated from this very chaotic core, violently flung out by powerful gravitational interactions with these massive, dominant objects. This pervasive, chaotic gravitational interaction extends its profound influence beyond just the stars themselves. It fundamentally shapes the nebula in its entirety, sculpting its very form. The intense, relentless radiation streaming from the trapezium cluster actively blows colossal bubbles into the surrounding gas, creating vast, intricate cavities and elaborate tunnels. These pathways, these cosmic channels, allow the potent ultraviolet light to escape unfocused. Directional blasts, like concentrated beams from a hidden lighthouse. These concentrated bursts of radiation are powerful enough to carve out towering pillars of gas and dust, create brightly illuminated rims around denser regions, and even trigger entirely new waves of star formation when they compress nearby gas clouds to critical densities. It's the ultimate feedback loop in action. The very stars being born are actively shaping the environment around them, an environment that, in turn, facilitates and even accelerates the birth of even more stars. It is a cycle of cosmic renewal. Another profoundly fascinating aspect of the trapezium cluster is its undeniable role in a phenomenon known as mass segregation. This is a process where the heaviest, most massive stars in a cluster tend to migrate or sink towards the center over time, while their smaller, lighter stellar siblings are progressively pushed or kicked away towards the cluster's outer edges. In the specific case of the trapezium cluster, this phenomenon appears to have occurred remarkably quickly, perhaps even before the cluster had fully coalesced into its stable, mature form. While it remains an active and intriguing area of scientific research, whether this rapid mass segregation is due to post-formation gravitational dynamics, the stars slowly settling over time, or to the very initial conditions of the cluster's birth, the result is unequivocally clear. The most massive and luminous stars are tightly packed into the core, reigning supreme over this vibrant stellar nursery, and directly influencing every aspect of the birth of new stars. Why is this important? Why does it matter how these massive stars are arranged? Because it fundamentally challenges and reshapes our traditional understanding of how star clusters evolve. If mass segregation is inherently built in from the very beginning, as the primordial hypothesis suggests, it strongly indicates that massive stars only form under very specific, highly dense central conditions, precisely in those deepest wells of gravitational potential within a collapsing gas cloud. It implies that the core of a forming stellar nursery may be almost pre-programmed to give birth to these colossal giants from the very outset. They are the initial architects of their own destructive beauty, and what magnificent giants they truly are. Theta 1 Orionis C, the undisputed dominant star of the trapezium cluster, with its mass approximately 40 times that of our Sun and emitting literally thousands of times more energy. Alongside other equally massive O and B-type stars nearby, completely redefines and dramatically reshapes their immediate environment. Their very existence generates ferocious ultraviolet radiation, powerfully strong stellar winds, and intense magnetic chaos throughout the surrounding nebula. In doing so, these giants perform a curious dual role. They both fuel and, paradoxically, suppress further star formation because they form first and sink deepest into the gravitational well. These are also the very stars most likely to dramatically alter or even violently destroy their surroundings by vigorously blowing away gas, brutally disrupting nascent planetary disks, and intensely heating the entire region. They are the powerful engines, but also the relentless sculptors. We can clearly observe how this profound influence plays out in Orion. The entire cloud is visibly flattened, intensely electrified, and fragmented around the trapezium cluster. These cosmic scars, these beautiful deformations, are the direct result of the immense radiation pressure exerted by these central dominant giants. But let's return to the question, why does this division, this segregation by mass, occur in the first place? One prevailing idea is based purely on dynamics. As the cluster grows and its constituent stars dynamically interact with each other, the heavier ones tend to lose kinetic energy through close encounters and naturally move closer together, like balls falling into a gravitational pool at the cluster's center. However, the Orion Nebula, being relatively young, estimated to be only 1 to 2 million years old, may not have had sufficient time for this purely dynamic process to fully complete and account for the observed extreme concentration. This is why many astronomers lean towards the hypothesis that the nebula's initial conditions, the very way the immense gas cloud collapsed and formed, inherently pushed most of its mass towards the center from the very beginning. It was set up from the start. Another compelling idea, one that resonates with the chaotic energy of Orion, is tied to competitive accretion. In this model, protostars that happen to be located in the dense central regions of a collapsing gas cloud have significantly more immediate access to the continuous flow of infalling material. They are positioned perfectly for growth. They grow larger and accrete mass much faster, essentially feeding voraciously from the environment like cosmic parasites with front-row seats at a celestial buffet. Stars at the periphery, by contrast, have access to less material and thus experience slower, more constrained growth. This inherent, natural imbalance directly results in the massive stars forming first in the core and quickly locking in their gravitational dominance. Their immense gravity can then actively disrupt the orbits of nearby smaller stars, sending them into elongated, chaotic paths, or even violently ejecting smaller objects entirely, transforming them into runaway stars or isolated brown dwarfs. Doomed to wander the galactic void alone, in this sense, the mass segregation observed in Orion isn't just a static arrangement of stars, a frozen snapshot. It's a dynamic, actively evolving system where the center wields immense power, shaping destinies, and the edges keenly feel the profound consequences of that central dominance. This clustering of massive objects at the core has tangible, far-reaching effects on the entire nebula. It significantly alters the lifespan of the nebula itself, because massive stars, by their very nature, burn through their fuel much more quickly and die young, often in spectacular supernovae that can literally tear the surrounding area apart, reshaping it entirely. The intense radiation from these central dominant stars can also photo-evaporate protoplanetary disks, fundamentally changing the very likelihood and nature of planet formation around their less massive siblings. Furthermore, it profoundly changes the overall form and structure of the entire cloud. The intricate interplay of overwhelming gravity and the fierce feedback from these giants carves out vast holes, delicate strands, powerful radiation walls, intricate filaments, and towering pillars in a magnificent cosmic sculpture, painstakingly carved by the relentless, creative, and destructive force of radiation. The nebula becomes a living, breathing artwork, shaped by the very forces within it. Let's allow our minds to float gently now, beyond the fiery core of the trapezium cluster, and direct our quiet attention to something truly remarkable: the faint, ethereal structures that whisper of creation, the cosmic ink drops seemingly suspended in the fiery air, little shadows wreathed in the edges of a brilliant, almost overwhelming glow. These incredible objects, which float near the very heart of the trapezium cluster, are known as proplids, a charmingly concise term for protoplanetary disks. Imagine them, these are, quite literally, solar systems still in their cosmic wombs, embryonic worlds taking shape. And the most astonishing part, we are able to see them coming together in the Orion Nebula, not as abstract theories, not as distant, vague simulations, but in real time, captured by cameras so exquisitely sharp they can cut through vast veils of dust and the blinding light from the emergent stars. It is an unparalleled glimpse into the very earliest moments of planetary genesis. Each proplid is, at its core, a young star, often incredibly young, perhaps less than 1,000,000 years old. This infant star is still lovingly wrapped in a vast, rotating disk of gas and dust. Think of it as a cosmic nursery, a celestial cradle, surrounded by the raw, fundamental materials of creation itself: hydrogen, the most abundant element, helium, its noble companion, various complex carbon compounds, the very building blocks of life, microscopic ice grains, hinting at future oceans and tiny silicate particles, the foundation of rocky worlds over the immense, patient spans of cosmic time. If such a delicate disk is fortunate enough to survive the harsh environment and persist long enough, the tiny particles within it begin a slow, gentle, yet utterly profound dance of accretion. First, microscopic grains softly stick together, building fragile bonds. Then, through countless collisions and gentle agglomerations, they gradually grow into pebbles, which, over eons, coalesce into mountain-sized planetesimals. Eventually, given enough time and undisturbed growth, these nascent building blocks can evolve into full-fledged planets, gracefully orbiting a central star, much like our own tranquil solar system. This, however, describes the ideal textbook scenario for planet formation: a serene, almost meditative, and largely undisturbed process. But in the Orion Nebula, the reality is far more challenging, far more dramatic, and infinitely more brutal than it might initially appear. Here, things are not serene. They are tough, unforgiving. These proplyds are not forming in some peaceful, isolated corner of space, far removed from cosmic turmoil. No, they are emerging, quite literally, within the very blast zone of the trapezium cluster, constantly bombarded by the intense, sterilizing, and destructive ultraviolet light streaming relentlessly from colossal, luminous stars like Theta 1 Orionis C. This relentless, invisible radiation acts with the devastating efficiency of a cosmic vacuum cleaner. It relentlessly strips the precious gas from these forming disks, heats it to thousands of degrees, and forcefully blows it off into the vastness of space in long, trailing flows, like celestial smoke. Indeed, if you observe many of the proplyds in Orion in high-resolution images, you will notice they possess distinct tails, strikingly reminiscent of comets. This is a direct visual testament to the radiation literally peeling back the outer layers of the disk, relentlessly turning its precious raw materials into vapor. This dynamic makes the Orion Nebula a place of profound, stark contrast. It is both a vibrant, fertile birthplace for worlds and a brutal, unforgiving battlefield where their very existence hangs by a thread. These nascent planetary systems are engaged in a desperate, silent race against time, frantically trying to gather enough dust and gas to collapse under their own gravity and form into planets before their essential raw materials are utterly destroyed, evaporated, or scattered by the very stars that illuminate the nebula with such breathtaking beauty. It's the cosmic equivalent of attempting to build a house during a ferocious sandstorm, with a flamethrower simultaneously aimed at your intricate blueprints. An almost impossible feat, yet one that miraculously sometimes succeeds. Yet, despite this profound, pervasive destruction, life, in the broadest cosmic sense, invariably finds a way. Dozens, perhaps even hundreds, of these fragile proplyds have been identified and observed in Orion, enduring against all odds. Some appear to be tightly packed and reassuringly thick, their disks showing minimal signs of erosion, suggesting they might still have a good chance of successfully forming planets. These are the hopeful ones. Others, however, are already visibly thinner, ghostly and translucent, indicating that much of their planet-forming material has been stripped away, leaving considerably less for the creation of new worlds. Their ability to survive, to persist against the relentless onslaught, seems to be directly correlated with their proximity to the trapezium cluster. The closer they are to its powerful, radiating heart, the stronger the destructive radiation, and consequently, the shorter their potential lifespan, their window of opportunity rapidly closing. Some proplyds are even observed to be dramatically surrounded by bow shocks. Magnificent, arc-shaped structures formed when the ferocious stellar wind from the central star slams directly and violently into the surrounding ionized gas, creating a visible glowing compression. These bow shocks serve as stark, luminous markers of the intense boundaries of stellar influence, starkly hinting at the sheer, unimaginable quantities of energy being violently thrown around in this chaotic nursery. It's akin to observing the complex, destructive interactions of 1,000 hurricanes, each possessing its own gravitational pull, its own rotational spin, and its own searing heat, all colliding in a grand ballet of destruction and creation, thanks to the incredible, tireless capabilities of the Hubble Space Telescope, and more recently, the even more powerful and revolutionary James Webb Space Telescope JWST. Astronomers have been able to peer deeper into the intricate structures of these proplyds than ever before, revealing their hidden secrets. In some, they have observed tantalizing gaps and rings within the dusty disks, tantalizing early signs of ongoing planet formation, little clearings carved by nascent worlds. These subtle yet profound features echo the structures we see in older, more evolved disks, such as those observed around stars in the Taurus star-forming region or in the famously detailed image of HL Tauri. Orion, however, offers us a unique, younger, and far more chaotic version of these fundamental processes, providing an unparalleled glimpse into what may have transpired before systems like our own even began to settle into their familiar, structured forms. It's a glimpse into our own deep past. These observations, these tantalizing hypotheses, are not merely pretty pictures for our detached enjoyment, nor are they abstract mathematical equations. They are profound hints about our own cosmic origins. It is entirely plausible, indeed highly probable, that our own solar system may have begun its existence in a place very much like the Orion Nebula. Imagine our sun, forming amidst intense radiation, in close proximity to massive, destructive stars, its primordial protoplanetary disk struggling fiercely to remain intact against the onslaught. There is even compelling evidence, painstakingly derived from meteorites found here on Earth, suggesting that debris from a nearby supernova event may have been violently incorporated into our early solar nebula. This implies that, much like the proplyds we observe valiantly struggling in Orion, we too were born in a chaotic, intensely active, and perhaps even violently clumpy stellar neighborhood. Therefore, when we quietly study the proplyds of Orion, we are not just contemplating the potential futures of other systems, wondering what might become of them. We are actively helping to decipher the profound, forgotten mysteries of our own deep past. Understanding the tumultuous genesis of our home, another intriguing possibility, a slightly more somber fate for some of these cosmic embryos, is that they might not form planets at all. If they lose too much material too quickly due to the relentless radiation, they may never accumulate enough mass to ignite nuclear fusion and become a star. Failing to reach that stellar threshold, instead, they might collapse into brown dwarfs or very low-mass stars. An entirely different evolutionary path still profoundly shaped by the relentless violence of their birthplace. Others might eventually birth rogue planets, solitary worlds violently ejected from their nascent systems during turbulent gravitational interactions, forever doomed to drift through the vast, cold interstellar medium of the galaxy, alone and without the comforting, guiding warmth of a sun. Each bright bead in Orion, each faint, dusty disk holds its own unique story, its own unfolding destiny, a whispered tale of becoming. Some are valiantly holding on, fighting for existence. A few are inevitably breaking apart under the cosmic strain. Some may already harbor colossal, forming worlds, perhaps even giant gas planets reminiscent of Jupiter, majestically taking shape deep within their protective dusty rings. We do not yet know the ultimate fate of each individual proplyd, each potential system, but we can, with our increasingly keen instruments, bear witness to their ongoing struggle, their dramatic fight for existence. One of the most amazing privileges of modern astronomy is that it allows us to observe, in staggering, intricate detail, how planetary systems are assembled in the very first, chaotic, and often violent moments of their formation. It is a front-row seat to the birth of worlds. Now, let us shift our tranquil gaze, allowing our minds to wander into another enigmatic corner of the Orion Nebula, a place populated by fascinating entities that often blur the very lines of cosmic classification, the brown dwarfs. These are abundant in Orion, representing a realm where celestial bodies make a valiant attempt to become stars, almost succeed, but ultimately fall just short of igniting the sustained nuclear fusion that truly defines a luminous star. Brown dwarfs are precisely these kinds of objects, these almost stars, and the Orion Nebula is teeming with them, a cosmic cradle for these elusive celestial bodies. Often, brown dwarfs are colloquially referred to as failed stars. However, this seemingly dismissive nickname truly doesn't do justice to their intrinsic strangeness, their unique, hybrid nature, and their profound importance in the cosmic scheme of things. They are not quite stars, primarily because they do not possess sufficient mass, typically less than 0.08 times the mass of our Sun, to sustain the fiery, energetic hydrogen fusion reactions that power our Sun and other brilliant main-sequence stars, allowing them to shine brightly for billions of years, but simultaneously. And this is crucial. They are also not planets, because they form through the same fundamental process as stars, the majestic gravitational collapse of vast clouds of gas and dust within a nebula. This places them in a peculiar cosmic identity crisis, a liminal state. They are too large to be classified simply as planets, yet too small to shine with the sustained, blinding brilliance of a true star. They exist in a category all their own, in the active, turbulent, and immensely fertile environment of the Orion Nebula. Brown dwarfs are surprisingly common, thanks to extensive infrared surveys and incredibly high-resolution imaging from powerful telescopes like Hubble, Spitzer, and most recently, the revolutionary JWST. Astronomers have been able to identify dozens, perhaps even hundreds, of these enigmatic objects. They often lurk, almost unnoticed by conventional telescopes, within the dusty, obscuring folds of M42 like smaller, quieter siblings nestled in the background, easily overlooked without the specialized infrared eyes of these advanced instruments. Many of these brown dwarfs are exceptionally young, some perhaps only a few million years old, still glowing with the residual heat of their birth. This youth makes Orion an unparalleled laboratory for studying how brown dwarfs form, how they evolve over time, and what the earliest phases of their peculiar lives truly entail. Unlike the older, cooler brown dwarfs that drift quietly through the vast, empty reaches of the galaxy, those found in Orion are still relatively warm from their tumultuous birth, providing invaluable, fresh clues to their origins and early development. Intriguingly, and somewhat surprisingly, like true stars, some of these young brown dwarfs are observed to be surrounded by their own rings of dust and gas, strikingly similar to the protoplanetary disks, or proplyds, we discussed earlier. This tantalizing discovery opens up the exciting and profound possibility that brown dwarfs, despite their dim, subdued nature, could potentially host their own miniature planetary systems, albeit ones that would be significantly smaller, much cooler, and bathed in a far fainter light than our own vibrant solar system. But how do these peculiar objects actually come into being? That is where the cosmic plot thickens even further, where certainty gives way to intriguing possibilities and ongoing scientific debate. One prevailing idea posits that brown dwarfs form in precisely the same manner as stars do from the gravitational collapse of vast, swirling gas clouds. The only difference, according to this model, is that these particular clouds simply never accumulate enough mass to reach the critical threshold for sustained nuclear fusion. They just fall agonizingly short of becoming true stars. Another compelling hypothesis suggests a more dramatic, almost violent origin, that brown dwarfs were once part of larger, developing stellar systems but were violently ejected from those systems due to powerful, chaotic gravitational interactions. This scenario is akin to a smaller, less fortunate participant being unceremoniously, forcefully thrown out of a crowded, bustling, and highly chaotic theater. Such a violent ejection could help explain why some brown dwarfs appear to drift alone, isolated in the vastness of space, seemingly unattached, while others remain in relatively close proximity to groups of stars, bearing the scars of their chaotic origins. In the dynamic, constantly churning environment of the Orion Nebula, we observe compelling evidence that appears to support both of these intriguing scenarios. Some brown dwarfs are found deeply embedded in the densest parts of the cloud, still surrounded by swirling gas and potentially still accreting material, a pattern consistent with the direct collapse model. Others are seen drifting solo, alone and far from the bustling action of the primary star-forming regions, as if they were indeed flung out during a colossal cosmic scuffle, a dance of gravitational forces, the incredibly chaotic gravitational soup of the trapezium cluster. With its tightly packed, immensely massive stars, could easily impart enough energy and momentum to toss a low-mass object across many light-years of space, sending it on a solitary journey, even more challenging to our existing classifications. Pushing the boundaries of our understanding, are some objects in Orion whose masses fall below the traditional brown dwarf threshold, dipping to as low as a few times the mass of Jupiter, the largest planet in our solar system. Yet, these objects still show clear evidence of having their own distinct disks of gas and dust, and possibly even forming moons or microplanets around them. Defying easy categorization, these extreme objects fundamentally challenge our very definitions of planet and star. Are they truly rogue planets, wandering aimlessly through the interstellar void without a parent star? Are they sub-brown dwarves, a newly recognized even lighter class of celestial body? Or are they simply planetary embryos that, for some reason, fail to find a stellar parent? Whatever their ultimate classification, they do not fit neatly into any existing category, underscoring the fact that Orion is a fertile breeding ground for cosmic rule breakers, for celestial anomalies that force us to rethink our cosmic order. Observing brown dwarfs directly is notoriously difficult, a true challenge for astronomers, primarily due to their intrinsic lack of significant visible light emission. They are dim, elusive. The most effective way to detect and study them is through infrared astronomy, where they're faint. Residual heat glows ever so slightly, a subtle cosmic whisper. Some brown dwarfs even exhibit unexpected flares and emit X-rays, providing tantalizing evidence that their magnetic activity can, in some ways, mirror that of much larger, more powerful stars. They are not merely inert balls of gas, static and unchanging. They are living, evolving entities, dynamic and changing, existing at the very edges of our understanding of stellar physics, constantly pushing the boundaries of what we thought was possible. And here's a truly surprising, almost counterintuitive fact, though: they may be incredibly dim and difficult to spot. Brown dwarfs might be numerically dominant in regions like Orion. That's right. It is entirely possible that there are more brown dwarfs than actual stars in some active star-forming regions, while they contribute far less light or heat to the overall cosmic budget. They add significantly to the total mass, subtly influencing the gravitational landscape. They fill in the gaps. They quietly shape the gravitational environment of the cluster. They are, in essence, the quiet cosmic majority, the unsung heroes of stellar populations. So, why do these enigmatic brown dwarfs matter so profoundly to our understanding of the universe? Because they blur the traditional, neatly drawn line between what we define as a planet and what we define as a star. This unique position makes them crucial to our comprehensive understanding of how everything, from the tiniest planets to the most colossal stars, ultimately forms and evolves. Are they merely an accidental byproduct of clustered star formation, a cosmic mistake, or are they a natural, inevitable consequence, an intrinsic part of the process? Do all nebulae produce them in such abundance? Or is Orion an unusually rich nursery for these substellar objects, And most tantalizingly, a thought to gently rest upon as you drift if these substellar objects can host their own planets or moons. Could they quietly, unnoticed, harbor life in dark, frozen systems, existing in a realm far beyond our conventional search for habitable worlds, waiting to be discovered? The Orion Nebula does not easily reveal its profound, deeply hidden secrets. But every brown dwarf we discover, every faint infrared glow detected in its depths, represents a new clue, another piece in the grand, intricate puzzle of cosmic formation. It's a testament to the immense range of outcomes that can occur when gas collapses under its own weight, demonstrating with quiet certainty that not every cloud is destined to ignite into a sun. And perhaps most poetically, most reassuringly, not becoming a sun does not mean becoming nothing. It means becoming something different, something unique, something equally important in the vast, beautiful tapestry of the cosmos. As we continue our gentle drift through the ethereal beauty of the Orion Nebula, let's now turn our soft gaze towards an even more fundamental, almost primal, aspect of this cosmic canvas, the very dust that pervades its luminous expanse. It might seem counterintuitive to focus on something as seemingly mundane as dust when discussing a place so vibrant and alive with light and creation. Yet, in the silent, swirling nurseries of the universe, cosmic dust is far from insignificant. It is the very bedrock of creation, the subtle, shimmering ingredient without which planets, and ultimately life, would simply not exist. Imagine it not as the dust that gathers on your windowsill, but as a fine, metallic, icy, and carbonaceous shimmer, perpetually dancing in the light of forming stars in the Orion Nebula. Dust is both a veil that obscures and a vital ingredient that brings forth new worlds. What exactly is cosmic dust? It's not quite like the dust on Earth, composed mostly of tiny fragments of human skin cells and lint. No, interstellar dust consists of microscopic solid particles, each typically no larger than a few hundred nanometers. That's 1,000 times smaller than a grain of sand. These tiny specks are born in the violent outflows of dying stars, or in the gentle, cooler atmospheres of red giants. Where heavy elements condense, they are composed primarily of silicates, much like the sand on Earth, but also significant amounts of graphite, amorphous carbon, iron, and a variety of complex organic molecules. Many are also coated in thin layers of ice. Especially in the cold, dense molecular clouds that serve as stellar nurseries. Think of each particle as a tiny, frozen, gritty, and chemically active building block, drifting silently through the void. In the vast, sprawling expanse of the Orion Nebula, dust plays a dual and profoundly important role. Firstly, it is a shield. The densest clouds of dust are opaque to visible light, much like a thick fog on Earth. This opacity is crucial. It acts as a protective blanket, shielding the colder, inner regions of molecular clouds from the harsh, destructive ultraviolet radiation streaming from massive, newborn stars. Without this protective shroud, the delicate process of gravitational collapse that leads to star formation would be constantly disrupted. The gas would be heated too quickly, dispersed too easily, preventing it from clumping together to form the dense cores required for stellar birth. So, paradoxically, the very thing that hides much of Orion's activity from our visible light telescopes is also the very thing that makes that activity possible. But the dust is more than just a shield. It is also a cosmic catalyst, a surface upon which the most intricate and crucial chemical reactions take place. In the frigid, almost absolute zero temperatures of space, gas phase chemical reactions are incredibly slow and inefficient. Atoms and molecules rarely collide with enough energy to react. However, when these atoms and molecules gently adhere to the surface of a dust grain, they become concentrated. They have more opportunities to meet, to interact, and to form more complex molecules It is on these tiny, dusty surfaces that some of the most fundamental organic molecules, the very precursors to life, are thought to be forged. Water, ammonia, methanol, even more complex prebiotic molecules, are believed to have originated on these cosmic grains before being released back into the gas phase. These molecules then become integrated into forming stars and, eventually, into forming planets. So, when you look at the dust in Orion, you are literally looking at the cosmic ingredients for life itself. Consider the interplay of dust and light in Orion. The brilliant, glowing portions of the nebula that we perceive in visible light are primarily regions where the gas has been ionized by intense ultraviolet radiation from the trapezium cluster. However, extending far beyond these luminous regions are vast, dark, and often invisible clouds of colder, neutral gas replete with even denser concentrations of dust. These are the dark nebulae within and around Orion, often seen as silhouettes against the brighter background, like the famous Horsehead Nebula. These dark lanes and patches are not empty. They are brimming with the densest accumulations of dust and molecular gas, marking regions of ongoing star formation that are still deeply shrouded from our direct view. It is within these dark, dusty cocoons that the next generation of stars is quietly, patiently, forming. The dust also plays a crucial role in the cooling of star-forming regions. As gas collapses, it heats up to continue collapsing and forming a star. This heat must be efficiently radiated away. Dust grains are excellent radiators of heat, particularly in the infrared spectrum. As gas molecules collide with dust grains, they transfer some of their kinetic energy, heating the grains. The grains then re-emit this energy as infrared radiation, allowing the gas cloud to cool and continue its inexorable gravitational collapse. Without this dusty cooling mechanism, many protostars would simply fail to form, unable to shed the excess energy needed to reach the critical densities required for ignition. So, in a very real sense, dust is an essential component of the cooling system for the universe's stellar furnaces. And what about the colors? The striking blues often observed around some stars in Orion are a direct result of how dust particles scatter light. This phenomenon is called Rayleigh scattering, and it's the same reason our sky appears blue on Earth. Smaller dust particles preferentially scatter shorter, bluer wavelengths of light more effectively than longer, redder wavelengths. Thus, when light from a very hot, blue star passes through a region with fine dust, the blue light is scattered towards us, making the region appear bluish while the red light continues onward, unimpeded. This creates the ethereal, shimmering blue veils that sometimes seem to drift across the nebula, guiding our eyes to regions where light meets matter in a delicate dance. The distribution of dust in Orion is far from uniform. It is sculpted by the very forces we have been discussing. The powerful stellar winds and intense radiation from the trapezium cluster literally blow away vast quantities of dust and gas, creating the large, hollowed-out cavities and intricate structures we observe. This process, known as photoevaporation, not only strips material from protoplanetary disks, but also clears out immense regions of the nebula, exposing the newly formed stars within. The edges of these cleared-out regions often appear as bright, sharply defined walls of gas and dust, intensely illuminated by the central stars. These luminous boundaries are where the dust is actively being eroded, creating a dynamic, ever-changing landscape. It's like watching an immense, slow-motion sandblasting operation taking place on a cosmic scale. Perhaps one of the most compelling aspects of cosmic dust in the Orion Nebula is its role in the formation of protoplanetary disks. These disks, as we discussed, are the cradles of future planets. The dust within these disks is crucial because it is the actual solid material that will eventually clump together to form the cores of rocky planets and the building blocks of gas giants. Without dust, there would be no solid surfaces, no planetary cores, no Earth. The composition of this dust, the ratio of silicates to carbon, The presence of various ice coatings directly influences the types of planets that can form in a system. The delicate dance of accretion within these dusty disks is often disrupted by the intense radiation from the trapezium. Yet, the survival of some of these disks, particularly those located in denser, more shielded regions, is a testament to the resilience of dust and the persistence of creation in even the harshest cosmic environments. So, the next time you see a stunning image of the Orion Nebula, remember the silent, unassuming hero within its luminous depths, the dust. It is the architect of shadow, the cradle of chemistry, the radiator of heat, the sculptor of light, and ultimately, the very foundation upon which worlds are built. It hides the birth of stars even as it provides the material for them. It is both the veil and the blueprint, an essential, yet often overlooked, component of the grand cosmic story. Without this ubiquitous, shimmering dust, the universe would be a far emptier, far less diverse place. The profound silence of the dust speaks volumes about its omnipresent role in shaping the cosmos, a role that unfolds quietly, patiently, within the gentle glow of the nebula. Now, let's allow our thoughts to gently drift towards another captivating aspect of the Orion Nebula, one that speaks to the continuous cycle of life and death, creation and destruction. Across the cosmos, the existence of shock waves and outflows. In the Orion Nebula, the concept of a gentle, quiet birth for a star is quickly dispelled. This is a region of immense, violent energy, where the forces of gravity and stellar feedback clash in a constant, dramatic ballet. Shock waves and powerful outflows are the visible manifestations of this cosmic violence. Yet, paradoxically, they are also fundamental to the very process of stellar creation. What exactly are these shock waves? Imagine a sudden, incredibly powerful explosion, or a cosmic hammer blow. When gas travels faster than the speed of sound through a medium, it creates a sudden, drastic change in pressure, density, and temperature. That's a shock wave. In Orion, these shock waves are generated by several powerful forces. One primary source is the stellar winds emanating from the massive, hot stars within the trapezium cluster. These winds are not gentle breezes. They are supersonic torrents of charged particles, blasting outwards at thousands of kilometers per second. When these high-velocity winds slam into the slower-moving, denser clouds of gas and dust that make up the nebula, they create immense, sweeping shock fronts. These fronts resemble colossal, shimmering arcs or walls, glowing as the gas within them is violently compressed and heated, emitting light across various wavelengths. Another significant source of shock waves comes from the outflows from very young, still-forming stars, known as protostars. As a protostar accretes material from its surrounding disk, it doesn't simply absorb all of it. Instead, a significant fraction of this infalling material is somehow channeled by the protostar's strong magnetic fields and ejected outwards in powerful collimated jets of gas. These jets, often traveling at hundreds of kilometers per second, smash into the surrounding molecular cloud, creating distinct, luminous knots of shocked gas known as Herbig-Haro HH objects. These HH objects are often found in pairs, extending outwards from the protostar in opposite directions, marking the pathways of these energetic outflows. They are like cosmic lighthouses, signaling the location of hidden stellar embryos. Why are these shock waves and outflows so important? Beyond their visual spectacle, because they play a crucial, dual role in star formation. On one hand, they are agents of destruction and dispersal. They can violently disrupt fragile protoplanetary disks, stripping away the gas and dust necessary for planet formation. As we discussed with the proplids, they can also prevent new stars from forming by dispersing smaller, less dense gas clumps before they can collapse. It's a powerful clearing mechanism, tidying up the cosmic nursery by blasting away excess material. This contributes to the overall star formation efficiency. Essentially, how much of the original gas cloud actually ends up in new stars? But on the other hand, and this is the paradox, Shockwaves and outflows are also powerful agents of creation and triggering. When a shockwave sweeps through a molecular cloud, it acts like a cosmic snowplow. It compresses the gas and dust ahead of it, increasing its density. If this compression is strong enough, it can push the gas over a critical density threshold, triggering a new wave of gravitational collapse and initiating the birth of new protostars. This is known as triggered star formation. Imagine a ripple in a pond, gradually building in height as it moves, until it becomes a powerful wave. In a similar manner, these cosmic shock waves can instigate new rounds of stellar creation, sometimes far from the original sources of energy. The outflows from protostars also serve a vital purpose in their own formation. Without these powerful outflows, the continuous infall of gas onto the protostar would lead to an accumulation of angular momentum. This would cause the protostar to spin faster and faster, eventually spinning itself apart before it could fully form. The jets act as a mechanism to shed excess angular momentum, allowing the protostar to continue accreting material and ultimately grow into a stable star. They are the cosmic exhaust pipes, preventing the engine from seizing up. Observing these phenomena in the Orion Nebula requires diverse astronomical tools. Optical telescopes capture the bright, glowing ionization fronts and the luminous Herbig-Haro objects. Infrared telescopes peer through the obscuring dust to see the warm gas and dust heated by the shocks, as well as the deeply embedded protostellar outflows. Radio telescopes can detect the specific molecular signatures in the cold, dense gas that is being compressed by these energetic events. The intricate patterns of these shock waves, the curved arcs, the bright filaments, the dark lanes, are not just aesthetic. They are a direct visual record of the ongoing, violent process of star formation. They trace the pathways of cosmic energy, showing us where matter is being compressed, heated, and redistributed. The presence of these pervasive shock waves and outflows makes the Orion Nebula a truly dynamic, ever-changing environment. It is a place of continuous cosmic demolition and construction. Old gas is cleared away, new gas is compressed, and in the midst of this ceaseless activity, stars are born, live out their brief, luminous lives, and eventually fade. The energy from the massive stars at the center ripples outwards, creating both beauty and destruction, shaping the very environment that gives rise to the next generation of stars. This continuous feedback loop of creation and destruction, mediated by the powerful forces of shock waves and outflows, is what keeps the Orion Nebula so incredibly active and vibrant. A perpetual stellar birth machine, it is a reminder that even in the vast, serene silence of space, there is immense, hidden power and constant, beautiful change. The universe is always in motion, always transforming. Let's allow our awareness to gently drift now, moving away from the violent shock waves and the fierce stellar winds, and settle upon the profound, almost overwhelming scale of the Orion Nebula. Particularly as it relates to time, when we gaze at this magnificent celestial tapestry, we are not just looking at a beautiful picture, we are looking deeply into the past, the light that reaches our eyes, the light that paints those vibrant colors and illuminates those cosmic dramas. Began its journey towards us some 300 years ago. Imagine that for a moment, 300 years. What was happening on Earth when those first photons embarked on their epic voyage across the vast emptiness of space? To truly grasp the concept of looking back in time, let's consider what that time frame means. Around 681 AD, when that light departed the Orion Nebula, the world on Earth was vastly different from our own, in the distant lands of Asia. The Tang dynasty was flourishing in China, a golden age of culture and innovation in Europe. The Byzantine Empire was still a dominant force, though facing new challenges, and the seeds of what would become modern nation-states were just beginning to sprout. In the Arabian Peninsula, Islam was expanding rapidly, transforming the geopolitical landscape. across the Americas. Complex indigenous civilizations thrived. Yet to encounter the outside world, there were no telescopes, no cameras, no understanding of light years. Humanity was still largely grappling with fundamental questions about its place in a geocentric universe. And as all these intricate human dramas unfolded, those tiny packets of light, those photons, began their silent, unwavering journey towards a future. Towards us. So, when we observe the Orion Nebula today, we are, in a very real and profound sense, seeing it as it existed in the 7th century, if just moments after that light left. A colossal event, perhaps one of the massive stars in the trapezium cluster went supernova, collapsing in a blaze brighter than a billion suns we would not know. Not yet. We would have to wait. We would continue to see its brilliant, stable light for another 1,300 years, oblivious to the cataclysm that had already occurred in that distant cosmic theater. This inherent time delay is a fundamental aspect of observing the universe. Every star, every galaxy, every wisp of gas we perceive is a relic of the past, a ghost of light. The farther we look out into space, the further back in time we are gazing. This concept of cosmic time, so different from our fleeting human experience, underscores the immense scale of the universe. Our lives are but a flicker, a breath, in comparison to the eons through which stars are born, live and die. A star like our sun lives for about 10 billion years. The massive stars in the trapezium cluster, with their profligate energy consumption, burn through their fuel in a mere few million years, perhaps only 5 or 10 million years in total. So, a star that began its life in Orion at the very moment the light we see today left would be less than 1/10 of the way through its brief, luminous existence before its light even reached Earth. This staggering difference in timescales invites a profound sense of humility and wonder. But the past we are observing in Orion is not a static, frozen moment. The nebula itself is a dynamic, evolving entity, constantly undergoing change. As we discussed, the shock waves ripple, the ionization fronts advance, and the proplids are continually sculpted and eroded. While these changes might seem slow on human timescales, they are rapid in astronomical terms. The subtle shifts captured by telescopes like Hubble over just a few decades are remarkable precisely because they show us cosmic evolution happening in something akin to real time for our instruments. This means that the 7th century Orion we are observing was itself a place of constant, vibrant transformation, an intricate cosmic dance that has been unfolding continuously for millions of years. Think of the processes of star formation within the nebula. The dense cores of gas that collapse to form protostars can do so incredibly quickly. Sometimes in as little as 100,000 years, that's a mere cosmic heartbeat. For these processes, 1 to 300 years is almost insignificant. It's less than 2% of the time it takes for a protostar to coalesce. This means that if a new star began to ignite in a deeply embedded, dusty part of Orion 1,000 years ago, we would still be waiting for its light to emerge from the surrounding obscuring clouds and then travel the vast distance to us. The birth of stars in Orion is a continuous process, a relentless cycle of creation, but our perception of it is always trailing behind, always observing the echoes of past events. This profound time delay also impacts our understanding of the present state of the nebula. When astronomers study the distribution of gas, the motion of stars, or the chemical composition, they are always interpreting data that reflects the nebula as it was in the past. To infer its current state requires sophisticated models and extrapolations. Taking into account the known rates of change, it's like trying to predict tomorrow's weather based solely on yesterday's forecast. We can do it, but there's always an inherent uncertainty. Yet, this uncertainty is also part of the allure, part of the endless fascination with the cosmos. It's a grand puzzle, constantly being reassembled with new pieces of light from the past The journey of these ancient photons across 1 to 300 light years is also a testament to the immense emptiness of space. For all that distance, for all that time, these light particles have traveled largely unhindered, carrying their pristine information from a distant era. They have crossed interstellar voids, navigated tenuous gas, and passed by countless other stars and galaxies, only to finally arrive at our detectors, delivering their timeless message. This uninterrupted voyage reminds us of the profound vacuum of space, allowing these messengers from the past to reach us largely intact, preserving their story across the eons. This journey through cosmic time, facilitated by light, also connects us deeply to the very origins of our own solar system. It is widely believed that our sun was also born in a turbulent, active star-forming region, much like the Orion Nebula. Approximately 4.6 billion years ago, imagine the chaos, the powerful winds, the intense radiation that our own protoplanetary disk might have endured. When we observe Orion, we are not just seeing a distant spectacle, we are witnessing a cosmic replay of our own genesis. We are looking at a living fossil, a cosmic time capsule that holds clues to the very conditions that gave rise to our sun, our Earth, and ultimately, ourselves. So, as you rest, let this concept of time wash over you. The light from Orion that caresses your eyes or your mind's eye tonight is a whisper from centuries past. A messenger from a time when human history was still unfolding in radically different ways. It's a gentle reminder that we are intrinsically connected to these vast cosmic processes, that the universe operates on scales of time that dwarf our own, and that every glance upwards is, in essence, a profound journey backwards, a communion with the ancient light of creation. Time, in the cosmos, is not a linear clock, but a layered tapestry, with each thread reaching back into an ever deeper past. And Orion, in its luminous splendor, is one of the most accessible and profound of these threads, inviting us to contemplate the quiet, majestic unfolding of cosmic history. Now, let's allow our minds to explore a slightly more speculative, yet utterly captivating aspect of the Orion Nebula, one that reaches beyond its immediate boundaries and into the grander narrative of galactic evolution. The idea that Orion is a cosmic trigger for future star formation, even beyond its current borders. We've spoken about the immense power of the stars within the trapezium cluster, their ability to ionize gas and create shock waves. But imagine these forces as ripples expanding outwards, not just within the nebula, but into the vast, darker, cooler molecular clouds that lie beyond its glowing edges. These ripples, these energetic impulses, can profoundly influence where and when the next generation of stars will begin to form in our galactic neighborhood. Think of it this way: the Orion Nebula is not an isolated island in space, it is a dynamic, highly active region within the much larger Orion molecular cloud complex. This complex, as we briefly touched upon, is a vast, interconnected network of cold, dense gas and dust that stretches across hundreds of light years. Most of this complex is dark, silent, and quiescent, seemingly inert. However, the immense energy being poured into the immediate environment by the stars in M42 acts as a profound disruptor and, paradoxically, a powerful stimulator for star formation in these surrounding, quieter regions. The primary mechanism for this triggering is the powerful shock waves and radiation pressure emanating from the massive O and B-type stars in the trapezium. As these forces expand outwards, they do two critical things. Firstly, they compress the surrounding cold, stable molecular clouds. Imagine a giant, invisible cosmic hand gently squeezing a sponge when gas and dust are compressed to a critical density. Their own internal gravity can overcome the internal pressure and thermal motions that usually keep them stable. This tipping point leads to gravitational collapse, initiating the formation of new stars. These new stars are not forming spontaneously, they are being nudged into existence. Their formation triggered by the external force of Orion's energetic output. Secondly, the expanding fronts of ionized gas, the beautiful, luminous edges of the nebula, can sweep up and accumulate matter as they advance. This accumulation of material creates dense shells of gas and dust that can also become gravitationally unstable and collapse. This is often referred to as the collect and collapse model of triggered star formation. The glowing boundaries of the Orion Nebula are not just pretty, they are actively shaping the future of star birth, pushing and pulling on the fabric of spacetime, creating the conditions for new suns to ignite. Evidence for this triggered star formation is observed throughout the Orion molecular cloud complex. For instance, you can see bright, distinct regions of new star formation that appear to be located at the very edges of the expanding HII region, the ionized hydrogen region of the Orion Nebula. The Horsehead Nebula, for example, a famous dark silhouette against a brighter background, is believed to be a dense, resilient pillar of gas and dust that is currently being eroded by the radiation from M42. But at its base, protected from the harshest radiation, new stars are indeed forming, seemingly triggered by the very forces that are sculpting its iconic shape. Similarly, regions further away, such as the monochorous R2 region, also show signs of triggered star formation, perhaps initiated by earlier generations of massive stars that once thrived in the Orion complex. This concept of triggered star formation is crucial for understanding the overall evolution of star clusters and galaxies. Stars don't just pop into existence randomly across the galaxy. Instead, star formation often occurs in propagating waves, where the birth of one generation of massive stars triggers the birth of the next generation in adjacent regions. The Orion Nebula is a prime example of such a process in action, a cosmic domino effect. It's current. Vibrant activity isn't just a snapshot in time. It's a powerful engine driving future stellar nurseries across a much wider region of our galaxy. Furthermore, this continuous triggering contributes to the hierarchical structure of star-forming regions. We see dense cores within larger clumps, which are part of even larger clouds. The energy feedback from massive stars, like those in the trapezium, plays a significant role in creating and maintaining this complex. Multi-layered structure. They are continually stirring, compressing, and shaping the interstellar medium, ensuring that the process of star formation is not a static event but a dynamic, self-propagating cycle. So, when we look at the Orion Nebula, we are not just seeing a past event or a current spectacle, we are observing a crucial link in the chain of galactic evolution. It is a powerful illustration of how the lives of massive stars, though brief and violent, leave a lasting legacy, sculpting the interstellar medium and seeding the conditions for the birth of future stars, future solar systems, and perhaps even future life, far beyond its immediate. Glowing boundaries. The Orion Nebula is, in essence, a cosmic heart, pumping life into the broader galactic neighborhood, setting the stage for future sunrises that we may never witness, but whose genesis we can subtly detect even now, in the faint whispers of gas and dust. It reminds us that the universe is not just a collection of isolated objects, but an intricately interconnected, continuously evolving system, where every event, every birth, every death, sends ripples far across the cosmic ocean. Setting in motion the next grand chapter of creation, let's allow our quiet contemplation to gently extend now, beyond the glowing heart of the Orion Nebula, and consider an even more expansive idea, the profound connection between Orion and the very origin of elements. It might seem a leap, from a star-forming region to the fundamental building blocks of the universe. But in truth, these concepts are deeply intertwined. Every atom of hydrogen in your body, every atom of oxygen in the air you breathe, every atom of iron in your blood, every atom of carbon that forms the basis of all life on Earth, all of these had a cosmic origin. And places like the Orion Nebula are not just birthing stars, they are, in a very real sense, the factories of the cosmos, tirelessly forging the elements that make up everything around us, including ourselves. Imagine, for a moment, the early universe. Just after the Big Bang, it was a remarkably simple place, almost stark in its composition. The vast cosmic soup consisted almost entirely of just two elements, hydrogen around 75% and helium around 25%, with trace amounts of lithium. There were no oxygen atoms, no carbon, no iron, no silicon, none of the heavier elements that are so crucial for rocky planets and complex life. So, where did all these heavier elements come from? They were forged inside stars. Stars are the alchemists of the universe. The process begins in the cores of stars like those in the trapezium cluster in Orion. These stars are undergoing nuclear fusion, a process where lighter atomic nuclei are fused together to form heavier ones, releasing immense amounts of energy in the process. In the cores of stars like our Sun, hydrogen fuses into helium, but in the much more massive stars found in Orion, the temperatures and pressures are far more extreme. These colossal stars are capable of fusing helium into carbon, carbon into oxygen, oxygen into neon, and so on, building up progressively heavier elements through a series of violent nuclear reactions. This stellar alchemy is a slow, methodical process during the star's main life. However, the truly heavy elements, those beyond iron on the periodic table, are not typically formed during the star's stable life. They require an even more cataclysmic event. When a massive star, like the O-type and B-type stars in the trapezium, exhausts its nuclear fuel, its core can no longer support itself against the crushing force of its own gravity. It collapses inward with incredible speed and violence, triggering a colossal explosion known as a supernova. This is one of the most energetic events in the universe, briefly outshining entire galaxies in the unimaginable temperatures and pressures generated during the supernova explosion. The conditions are finally met to forge the very heaviest elements, such as gold, silver, uranium, and lead. Through processes like the rapid neutron capture process, our process. And here's where Orion connects so profoundly to our existence when these massive stars eventually go supernova. They don't just create these elements, they disperse them back into the interstellar medium. The shock waves from the supernova explosion violently eject these newly forged heavy elements, along with vast quantities of hydrogen and helium, into the surrounding space. This enriched material then mixes with the existing gas and dust in the nebula, gradually increasing the metallicity, astronomers' term for the abundance of elements heavier than hydrogen and helium of the gas cloud. So, the next generation of stars that forms from this enriched material will contain a higher proportion of these heavier elements. And, crucially, if those stars are accompanied by protoplanetary disks, those disks will also contain these vital ingredients. Our own Sun is a second-generation or even third-generation star, meaning it formed from gas and dust that had already been enriched by previous generations of massive stars that lived and died in supernova explosions. The heavy elements that make up Earth, and indeed, every atom in your body, were once forged in the fiery hearts of long-dead stars, scattered by supernova, and then incorporated into the nebula from which our solar system eventually coalesced. The Orion Nebula is a living laboratory for observing this cosmic cycle in action. While the current massive stars in the trapezium cluster haven't yet exploded as supernovae, they are too young. Just a few million years old, they are diligently fusing lighter elements into heavier ones in their cores. When their time comes, in a few million years, they too will explode, showering the surrounding space with newly forged elements, further enriching the Orion molecular cloud complex. This enriched material will then become the raw ingredients for the next generation of stars and planets. This is the continuous galactic chemical evolution at play. Astronomers study the spectral signatures of elements in the Orion Nebula's gas and dust to understand its chemical composition. By analyzing the unique wavelengths of light emitted or absorbed by different elements, they can map the distribution of carbon, oxygen, nitrogen, sulfur, and other heavier elements throughout the nebula. This helps them understand how effectively these elements are being recycled and how quickly the interstellar medium is becoming enriched. The presence of complex organic molecules in the dusty disks around protostars and Orion is a direct testament to this chemical enrichment, hinting at the molecular complexity that can arise even in these harsh environments. So, as you rest, let this profound truth sink in the light and colors you imagine from the Orion. Nebula are a reflection of ongoing element formation. The immense energy of its massive stars is not just for show, it is a testament to the universe's tireless engine of creation, converting simple hydrogen and helium into the complex symphony of elements that makes life possible. Orion is not just a place where stars are born, it's a cosmic forge, ceaselessly building the very atoms that flow through our veins, the atoms that form the planets beneath our feet, and the atoms that make up the distant stars themselves. It's a reminder that we are, quite literally, made of stardust, recycled across cosmic generations. A profound and beautiful connection to the very heart of creation. Let's gently transition our focus now to an idea that might feel both vast and incredibly intimate, the concept of Orion as a cosmic mirror, reflecting the birth of our own sun and solar system. It's a powerful thought to consider, that in this distant, turbulent nebula, we might be witnessing a profound echo of our own ancient origins, a glimpse into the chaotic crucible from which our quiet, stable home emerged billions of years ago for a long time. Astronomers debated whether our sun was born in isolation, far from other stars, or if it formed within a crowded, active stellar nursery, the prevailing scientific consensus, supported by a wealth of evidence, now points strongly towards the latter. Our sun, a seemingly solitary star in its current state, was almost certainly born in a dense, bustling star cluster. Much like the ones we see forming in the heart of the Orion Nebula today, why do scientists believe this one crucial piece of evidence comes from meteorites that fall to Earth? These ancient cosmic rocks are essentially pristine remnants from the very early solar system. When scientists meticulously analyze their composition, they find traces of certain isotopes of elements, such as aluminum-26 and iron-60, that are relatively short-lived radioisotopes. These isotopes could only have been produced in significant quantities by a very specific event, a nearby supernova explosion that occurred just as our solar system was beginning to form. Or perhaps even a little before. Scattering these rare elements into the nascent solar nebula for a supernova to occur, there must have been at least one very massive star nearby, a star that lived a short, brilliant life and then spectacularly died. Massive stars like these are not born in isolation. They typically form in large, dense clusters. Therefore, the presence of these supernova fingerprints in our solar system's earliest materials strongly implies that our sun was born in such a crowded, active, and indeed, violent stellar nursery, a place brimming with other young, massive stars. And what better modern-day analog for such a birthplace than the Orion Nebula Orion, with its tightly packed trapezium cluster of massive O and B-type stars, its myriad of young, developing protostars, its swirling protoplanetary disks, the proplyds, and its pervasive shock waves and intense radiation, provides a living, breathing model of the conditions that likely existed when our sun was formed. The fierce ultraviolet light, the powerful stellar winds, the gravitational interactions, all of these forces that we observe sculpting and shaping Orion today would have been part of our sun's birth environment. Imagine our own nascent sun, then a humble protostar, enveloped in its own swirling disk of gas and dust. Much like the proplyds we discussed, this tiny, vulnerable solar system embryo would have been bombarded by the intense radiation from its massive stellar neighbors. Perhaps even experiencing the powerful shockwave from a supernova, it would have been a chaotic, high-energy environment, a far cry from the serene, distant void where our sun now quietly resides. The fact that our planet Earth eventually formed, and life subsequently arose, within such potentially turbulent beginnings is a profound testament to the resilience of creation. When we observe the proplyds in Orion being actively eroded by radiation, with their distinctive comet-like tails of evaporating gas, we are witnessing a process that very likely shaped our own early solar system. Perhaps our protoplanetary disk lost a significant amount of its initial material due to similar photoevaporation, influencing the final masses and compositions of our planets. The gaps and rings observed in some of Orion's proplyds could be seen as direct analogs to the early stages of planet formation in our own system. Where protoplanets were already beginning to clear out pathways in the dusty disk, the presence of brown dwarfs in Orion also strengthens this connection. If our sun was born in a cluster, it would have had thousands of stellar siblings, ranging from massive O-stars to tiny brown dwarfs, all vying for gravitational dominance and contributing to the overall dynamics of the nursery. Our understanding of how brown dwarfs form, whether through direct collapse or violent ejection, offers clues to the full spectrum of outcomes in a stellar nursery, including the potential for runaway objects like the ones our sun might have encountered, or even been responsible for ejecting. In its earliest, most turbulent phase. So, Orion is not just a distant, beautiful spectacle. It is a cosmic time machine, allowing us to glimpse the conditions of our own violent, yet incredibly fertile, birth. It provides a living laboratory to test theories about how stars and planetary systems form in crowded, active environments. By understanding the processes unfolding in Orion today, we gain invaluable insights into the very earliest moments of our solar system's history, shedding light on the tumultuous conditions that ultimately led to the stable, life-supporting planetary system we call home. It's a profound thought. The light from a distant nebula, a whisper from the deep past, holds the secret to our own beginning, linking us directly to the grand, ongoing saga of cosmic creation. We are all, in a very real sense, children of a nebula, and Orion is helping us remember our cosmic lineage. Let's allow our minds to gently explore another layer of the Orion Nebula's intricate beauty, one that speaks to the very heart of how we perceive the universe, the subtle yet profound interplay of colors and light. When we gaze upon the awe-inspiring images of Orion, our eyes are captivated by the vibrant reds, the ethereal blues, and the soft, almost ghostly greens. These are not merely artistic embellishments. They are a direct visual language, a cosmic code revealing the nebula's very composition, its temperature, and the dynamic processes unfolding within its luminous embrace. Imagine the nebula not as a static painting, but as a living, breathing tapestry of light, woven from the fundamental elements of the cosmos. The most dominant and pervasive color you encounter in Orion is a deep, resonant red. This is primarily due to the ubiquitous presence of hydrogen gas, the universe's most abundant element, as we gently explored before. The energetic ultraviolet radiation from the colossal stars in the trapezium cluster strips electrons from hydrogen atoms, a process called ionization, when these electrons eventually fall back into orbit around their parent protons. They release energy in the form of light, specifically at a characteristic wavelength of 656.3 nanometers. This particular emission is known as H-alpha, and it is the signature of ionized hydrogen. It's the universe's most common and powerful way of showing us where active star formation is occurring, where gas is being energetically excited. So, whenever you see that glorious red, know that you are witnessing the fundamental process of hydrogen atoms being transformed and then returning to a state of equilibrium, releasing their quiet, crimson light. But the palette of Orion is far richer than just red, interspersed with the deep reds. You'll often see wisps and veils of a beautiful, almost otherworldly blue. This blue light originates from a different process and a different element. It is primarily emitted by ionized oxygen. When oxygen atoms are excited by the energetic photons from the trapezium stars, they can emit light at specific wavelengths in the blue-green part of the spectrum, notably at around 500.7 nanometers. This blue color is often more pronounced in regions where the oxygen is highly energized, typically closer to the hottest. Most luminous stars, it adds a delicate, almost ghostly quality to the nebula's appearance. A subtle counterpoint to the more dominant red. Beyond these emission lines, there's another crucial way light interacts with the nebula reflection. Some parts of Orion appear blue, not because the gas itself is emitting blue light, but because it is reflecting it. Imagine a fine mist in front of a bright blue lamp. The mist itself isn't glowing blue, but it scatters the blue light towards your eyes. Similarly, regions within Orion that contain significant amounts of fine dust, located near bright, hot, blue stars, will scatter the starlight, as we explored with cosmic dust. Smaller particles preferentially scatter shorter, bluer wavelengths of light more effectively than longer, redder wavelengths. This phenomenon, known as Rayleigh scattering, is the same principle that makes Earth's sky appear blue. So, the ethereal blue areas in Orion can often be reflection nebulae, where starlight is simply bouncing off the cosmic dust, painting a shimmering blue veil across the void. Sometimes, too, you might discern faint hints of green or even deeper, more subtle hues. These often come from other elements like ionized sulfur or even trace amounts of other excited elements. Each element, when energized, acts like a unique tuning fork, vibrating and emitting light at its own distinct set of wavelengths. By meticulously analyzing the full spectrum of light emanating from different parts of the nebula, astronomers can create detailed maps of its chemical composition, its temperature distribution, and its density. It's like having a cosmic microscope that can reveal the very atomic makeup of this distant cloud. It's important to remember that our human eyes have limitations. The stunning, vibrant colors we see in popular astronomical images of Orion are often the result of sophisticated photographic techniques involving long exposures and narrowband filters. These filters are designed to isolate specific wavelengths of light, allowing astronomers to capture the faint emissions from particular elements. Without these techniques, the Orion Nebula appears as a much dimmer, grayish-green smudge to the naked eye, even from very dark locations. Our eyes, while marvelous, cannot gather enough light over time, nor are they sensitive enough to the deep red H-alpha emission, which is visually one of the most important components of the nebula's light. So, the colors you admire are a scientific translation, a revealing of light that whispers below the threshold of normal human perception. The interplay of these colors is a dynamic process. The intense radiation from the trapezium cluster not only excites the gas but also sculpts the very distribution of the dust and gas, creating the intricate patterns of light and shadow where the radiation is strongest. Hydrogen emission dominates, painting vibrant reds where dust is plentiful and scattering light. Blues emerge, where a different balance of elements or energy exists. Subtle greens or oranges might appear. The nebula is a masterpiece of light and chemistry, a living canvas perpetually being painted by the forces of stellar birth and death. So, as you rest and imagine the Orion Nebula, do not just see its beauty, see its story. See the hydrogen glowing red, whispering of endless cosmic transformations. See the oxygen shining blue, echoing the ethereal dance of ionized atoms. See the scattered light, hinting at the cosmic dust that cradles future worlds. Each color is a gentle, silent note in the grand symphony of the universe. A visual poem about the very nature of light, matter, and creation itself. It's a reminder that even in the vast silence of space, there is a profound, eloquent language written in light, waiting for us to perceive its subtle, calming messages Let's now allow our thoughts to gently expand further, beyond the visible grandeur of the Orion Nebula, and contemplate its place within the grander, almost unimaginable tapestry of the Milky Way galaxy. Orion is not just a spectacular individual object, it is a vital, dynamic component of our home galaxy, a microcosm reflecting the immense processes that shape galactic evolution. It is one small, yet incredibly active cog in the colossal machinery of our spiraling stellar island. The Milky Way is a majestic spiral galaxy, a vast collection of hundreds of billions of stars, along with immense clouds of gas and dust, dark matter, and cosmic rays, all bound together by the relentless pull of gravity and rotating gracefully around a central supermassive black hole. Our Sun, along with our entire solar system, resides in one of the Milky Way's minor spiral arms, specifically known as the Orion Arm, also sometimes called the Local Arm. This is significant because the Orion Nebula itself is located within this very arm, a mere 1,300 light-years away. This proximity makes it one of the closest and most prominent massive star-forming regions to our solar system, within spiral galaxies like the Milky Way. Star formation doesn't occur uniformly throughout the galactic disk. Instead, it is largely concentrated within the spiral arms. These arms are not rigid structures, like the spokes of a wheel instead. They are more akin to density waves regions, where gas and dust are temporarily compressed as they orbit the galactic center. Imagine a traffic jam on a highway. The cars aren't permanently stuck, but they slow down and bunch up in certain areas. Similarly, as molecular clouds drift into these spiral density waves, they are compressed, triggering the collapse of gas and dust, and initiating the birth of new stars, the Orion Nebula. Situated in our local arm, is a prime example of such a star-forming factory being stimulated by the galactic environment. The immense scale of our galaxy is difficult to fathom. The Milky Way spans approximately 100,000 to 200,000 light-years across and is perhaps 1,000 light-years thick. Our Sun is located about 2/3 of the way out from the galactic center, some 27,000 light-years away. It takes our solar system roughly 230 million years to complete one full orbit around the galactic center, a period known as a galactic year in this vast dynamic system. Regions like Orion act as powerful engines of renewal, continuously recycling interstellar material and creating new generations of stars. The materials that form stars and planets in places like Orion are not simply static reservoirs. They are part of the vast, intricate interstellar medium, ISM, of the galaxy, a diffuse mixture of gas, dust, and cosmic rays that fills the space between stars. This ISM is constantly being stirred, enriched, and recycled. Stars are born from it. They live out their lives, and then, through stellar winds and supernova explosions, they return processed material, including newly forged heavy elements, back into the ISM. This enriched gas then becomes the raw material for the next generation of stars. The Orion Nebula is a vibrant demonstration of this galactic recycling program in full swing. The massive stars of the trapezium cluster are actively blowing away vast quantities of gas and dust, enriching the surrounding ISM with the elements they have already fused in their cores, setting the stage for future star birth in other parts of the arm. Furthermore, the activity in regions like Orion has a broader impact on the galaxy. The powerful supernova explosions that will eventually mark the deaths of the massive stars in the trapezium cluster will not only disperse heavy elements, but also generate enormous shock waves that can propagate across hundreds of light years. These shock waves can compress distant molecular clouds, potentially triggering new waves of star formation far from Orion's immediate vicinity. This demonstrates how localized events within a spiral arm can have cascading effects, contributing to the overall pattern of star formation throughout the galaxy. The galaxy is a symphony, and Orion is one of its loudest, most vital instruments, orchestrating change far beyond its immediate reach. The study of Orion helps astronomers understand the evolution of spiral galaxies by observing how stars form, how gas is dispersed, and how elements are enriched in a nearby active region. Scientists can infer similar processes in more distant, unresolved galaxies. Orion acts as a kind of Rosetta Stone for galactic astronomy, providing a detailed close-up view of processes that are fundamental to how spiral galaxies maintain their structure, replenish their star populations, and evolve over billions of years. It helps us understand how our own galaxy has evolved and how it will continue to change in the future. In essence, the Orion Nebula is a powerful reminder that our galaxy is a living, breathing entity, constantly transforming itself through cycles of creation and destruction. It is not just a collection of static stars, it is a dynamic, interconnected system where every star-forming region, every supernova, every swirling cloud of gas and dust plays a role in the grand, ongoing saga of galactic evolution. As you rest, let this immense scale gently wash over you. You are part of a galaxy, and the light from Orion, a beacon in your own galactic arm, is a quiet whisper, connecting you to the ceaseless, majestic rhythms of the Milky Way, a reminder of the boundless, beautiful transformation that defines our cosmic home. Let's allow our minds to gently settle on a truly remarkable and somewhat humbling aspect of the Orion Nebula, its profound significance as a celestial laboratory for scientific discovery. For astronomers, Orion isn't just a distant, beautiful spectacle, it's an indispensable outdoor classroom, a natural workshop where we can test our theories, refine our models, and uncover the fundamental laws governing the universe, its proximity, its dynamic activity, and its sheer brilliance make it an unparalleled arena for scientific exploration. Why is Orion such a vital laboratory, firstly? Its relative closeness to Earth, a mere 1/300 light-years away, is a game-changer. While 300 light-years sounds immense, in astronomical terms, it's practically on our doorstep. This proximity means that our most powerful telescopes, like the Hubble Space Telescope and the James Webb Space Telescope, can resolve an unprecedented level of fine detail within the nebula. We're not just seeing blurry blobs, we're seeing individual young stars, intricate structures within protoplanetary disks, and the subtle dance of gas and dust being sculpted by powerful forces. This clarity is crucial for understanding processes that would remain completely hidden in more distant star-forming regions. Secondly, Orion is a perfect example of an active star-forming region. It's not a static, finished product. Stars are being born there right now. From the very first moments of gas cloud collapse to the fiery ignition of massive O-type stars. This allows astronomers to study every single stage of stellar evolution in a single location. We can observe dense, cold clumps of gas beginning to collapse, protostars still deeply embedded in their dusty cocoons, newly ignited stars clearing away their birth material, and even the failed stars known as brown dwarfs. It's like having a time-lapse video of starbirth playing out before our eyes, allowing us to piece together the entire complex narrative. One of the most exciting areas of research in Orion is the study of protoplanetary disks, or proplids, because Orion is so close. Telescopes like Hubble and JWST can resolve these disks with enough detail to detect structures within them, such as gaps and rings. These features are thought to be direct evidence of planets forming within the disk, clearing out paths as they accrete material. Studying the proplids in Orion allows scientists to understand how planets form in highly energetic, radiation-rich environments, which might have been similar to the conditions our own solar system faced billions of years ago. It's a living blueprint for planetary genesis. Orion is also an ideal testing ground for theories about stellar feedback. This is the process where the energy, radiation, and winds from newly formed massive stars impact their surroundings. influencing subsequent star formation. In Orion, we can directly observe how the powerful ultraviolet radiation from the trapezium cluster is eroding gas, creating spectacular pillars and cavities, and perhaps even triggering new generations of stars in adjacent regions. These observations provide crucial data to refine complex computer simulations that model how star formation proceeds in galactic environments. Without Orion, validating these theoretical models would be far more challenging. Furthermore, the nebula offers a unique opportunity to study the role of turbulence and magnetic fields in star formation. As we discussed, the gas within Orion is a chaotic maelstrom with supersonic flows and intricate magnetic field lines. By observing the motion of gas and mapping the magnetic fields through phenomena like polarization of light, astronomers can understand how these forces influence the collapse of gas clouds and the final masses of the stars that form. This is incredibly complex physics, and Orion provides the clearest, most detailed natural laboratory for it. The chemical complexity of the Orion Nebula also makes it a rich target for astrochemistry. Scientists use spectroscopy to analyze the light from different parts of the nebula. Identifying the unique fingerprints of various molecules, they've found a surprising array of complex organic molecules, including those considered precursors to life. Studying where and how these molecules form in Orion helps us understand the chemical pathways in space and the potential for life to arise elsewhere in the universe. It tells us about the cosmic ingredients available for planetary systems forming in such regions. Finally, Orion serves as a benchmark for astronomical instruments and techniques because it's so bright and well studied. New telescopes and instruments are often pointed at Orion first to calibrate them and demonstrate their capabilities. Its familiar features allow astronomers to compare new data with decades of previous observations, ensuring the accuracy and reliability of their instruments. It's a cosmic tuning fork for our scientific tools. So, when we look at the Orion Nebula, we are not just witnessing a beautiful cosmic ballet, we are observing an ongoing, real-time experiment, a vast natural laboratory where the most fundamental processes of the universe, the birth of stars, the formation of planets, the creation of elements are playing out before our very eyes. It is a place where scientific inquiry thrives, continually pushing the boundaries of our understanding and deepening our appreciation for the intricate wonders of the cosmos. Let's conclude our profound journey through the majestic Orion Nebula by allowing our minds to reflect on its enduring legacy and future evolution. The Orion Nebula, this vibrant tapestry of gas, dust, and nascent stars, is not a static monument frozen in time. It is a dynamic, living entity, constantly changing, continuously shaping the future of its cosmic neighborhood and, in a larger sense, our galaxy itself. Its current brilliance is merely one fleeting moment in its grand, ongoing story. The future of the Orion Nebula is intrinsically linked to the fate of its most massive stars, particularly those in the trapezium cluster. These stellar giants, burning through their nuclear fuel at an astonishing rate, are living brief, furious lives. While they are currently illuminating and sculpting the nebula with their powerful radiation and stellar winds, their end will be even more dramatic. In a few million years, a blink of an eye in cosmic time, these colossal stars will exhaust their fuel and collapse, culminating in spectacular supernova explosions. When these supernovae occur, they will unleash an unimaginable amount of energy, briefly outshining entire galaxies. These explosions will have a profound impact on the Orion molecular cloud complex. They will violently disperse vast quantities of gas and dust, scattering the heavy elements forged within their cores back into the interstellar medium. This will further enrich the surrounding region, providing the raw material for future generations of stars. However, these powerful blasts will also disrupt and potentially destroy any remaining protoplanetary disks and young star clusters in their immediate vicinity. It's a violent, yet ultimately creative, act of cosmic recycling. Following these cataclysmic events, the current visible glow of the Orion Nebula, powered by the trapezium stars, will eventually fade. The intense ionization that gives it its brilliant colors will diminish as its primary energy sources disappear. Over tens of millions of years, the remaining gas and dust will continue to disperse and become less dense, likely blending into the background of the Orion arm. The nebula as we know it today will cease to exist, becoming a ghostly memory in the cosmic landscape. However, the legacy of the Orion Nebula will persist in several ways. Firstly, the newly formed stars that have successfully emerged from its dusty embrace will continue their long lives, eventually scattering throughout the galaxy. Our own sun and solar system, which likely formed in a similar environment, are a testament to this enduring legacy. The thousands of stars currently forming in Orion, from sun-like stars to brown dwarfs, will populate our galaxy for billions of years to come. Secondly, the supernova explosions from Orion's massive stars will not only enrich the interstellar medium, but also generate powerful shock waves that will trigger new waves of star formation in other, currently quiescent, parts of the Orion molecular cloud complex and beyond. This propagation of star birth, where one generation of massive stars gives rise to the next, is a fundamental process in galactic evolution. So, even as the current Orion Nebula fades, its energy will have seeded the birth of countless future stars and planetary systems throughout our galactic arm. Finally, the most enduring legacy of the Orion Nebula, for us, lies in the knowledge and understanding it has provided. It has served as an unparalleled laboratory, offering scientists a close-up, real-time view of star and planet formation. The data gathered from Orion has fundamentally reshaped our understanding of astrophysics, informing our theories about stellar evolution, planetary formation, galactic dynamics, and astrochemistry. Its role as a benchmark for astronomical instruments and a testbed for new theories will continue to influence scientific discovery for generations. So, as we conclude our imaginative journey, let's carry with us the profound understanding that the Orion Nebula is more than just a beautiful collection of gas and dust. It is a living, breathing testament to the universe's ceaseless cycles of creation and destruction. A cosmic factory churning out stars and potentially planets, and a vital link in the grand chain of galactic evolution. Its light, traveling across millennia, brings us a message not just from the past, but about the very future of our cosmos. It is a reminder that even as things change and fade, their energy and their essence persist, transforming into the next grand chapter of the universe's unending story. This marks the end of our exploration of the Orion Nebula. I hope this journey has been as enlightening and awe-inspiring for you as it has been for me. Would you like to explore another cosmic wonder? Or perhaps delve deeper into a specific aspect of the universe?